Good morning. Hello. Good morning, everyone. Good morning. Good morning.
अच्छा इसको घुमाने में भी तकलीफ होगा इसमें सिग्नल ही आ रही
A very good morning. So, Professor John Barbier has also joined. I welcome you, sir. So, we are just starting. Are we okay? Am I audible to all?
Yes, very well.
Okay. Thank you. Thank you. Respected Chief Guest, Professor GIAN Chakrabarti, Honorable Dean RC, Professor Rohit Mehra, HOD IT, Dr. Vijay Chahar, HOD EC, Dr. Ashish Raman, GIAN Coordinator, Dr. Vimal, Course Coordinator Deepti, Course Coordinator me, Dr. Jaspal. I welcome you all on behalf of Dr. B.R. Ambedkar, NIT Jalandhar, and I really express a very warm welcome and a cordial good morning to all of you. Good morning, everyone. It gives me immense pleasure to welcome you all in the inaugural ceremony of GIAN course titled Information Theory and Mean Field Theory of High Dimensional Bayesian Inference, being hosted under the prestigious grant Global Initiatives of Academic Networks, an initiative of Ministry of Education, Government of India, which aims at tapping of talent and pool of scientists and academicians internationally to enhance the quality of higher education and research in India. We are also honored today to have Dr. GIAN Barbier from ICTP Italy with us to conduct the course. I welcome you, sir, on behalf of my institute, Dr. B.R. Ambedkar, NIT Jalandhar. So now, may I request HOD IT, Dr. Vijay Chahar, and HOD EC, Dr. Ashish Raman, to kindly present a token of welcome to Professor GIAN Chakrabarti, sir. Thank you, sir. May I now request Professor Harsh Verma and Dr. Deepti Kakkar to kindly join and present a token of gratitude to Dean RC, Professor Rohit Mehra. Sir, please, ma'am. May I now request Dr. Deepti to kindly join and to present a token of gratitude to HOD EC Dr. Ashish Raman. Sir, please. May I now request Deepti Kakkad ma'am to kindly felicitate HOD IT Dr. Vijay Chahar. Put a huge round of applause, sir. May I now request Dr. Deepti Kakkad to kindly felicitate our GIAN coordinator Dr. Vimal sir. I welcome all the online participants who have joined us today for the inauguration purpose, and I also welcome all of offline participants who have expressed their sincere request and interest to join us offline into the inauguration of GIAN course on information theory. I welcome you all, everyone. So now, moving forward, may I now request all the dignitaries to kindly join us for the inauguration, that is a traditional inauguration of starting of an event with the lamp lightning. So may I now request Professor J.M. Chakrabarti, Professor Harsh Verma, HOD EC Dr. Ashish Raman, HOD IT Dr. Vijay Chahar, GIAN Coordinator Dr. Vimal, Dean RC Dr. Rohit Mehra to kindly please join to light the lamp. And I also welcome Professor Sangal sir to the GIAN course. Sir, please join us in the lightning of lamp.
मैम आप दोनों उधर चले जाओ मैम
ठीक है
नेत्रा भाई इधर से खींच इधर से सामने आएगी
पार्टिसिपेंट पार्टिसिपेंट को बुलाओ किसी को बुलाओ पार्टिसिपेंट को पार्टिसिपेंट को बुलाओ हाँ वही बोल दो हेलो ये नहीं बोल
Thank you.
Thank you.
बुझाना मत ना,
मुझे आना मत, चलो रहने दो।
चलने दो,
मुझे
चलने दो।
Thank you, everyone. So, may I now request Dr. Vimal, who is the local GIAN coordinator for Dr. B.R. Ambedkar and NIT Jalandhar, to kindly express an introduction to GIAN courses, which is conducted by Ministry of Education, Government of India. So, I request you to please present a introduction to GIAN courses, sir, please.
A very good morning to all of you. Honorable Director, NIT Jalandhar, Professor Vinod Kumar Kanodia. He could not be present today because of some prior occupancies. So today's chief guest, Professor GIAN Chakravarti, Officiating Director, NIT Jalandhar. International Course Instructor, Dr. John Barbier. Dean RC Professor Rohit Mehra, Professor Sangal, Professor Harsh Verma, Head of the IT Department, Dr. Vijay Chahar, and Head of EC Department, Dr. Ashish Raman, the Course Coordinator, Dr. Jaspal Kaur Saini, and Dr. Deepthi Kakkar, dear faculty members, students, and participants. On the behalf of GIAN program and INIT Jalandhar, I welcome you all to this 7th GIAN course organized by Department of Information Technology and Department of Electronic Communication and Engineering. The program GIAN, that is Global Initiative of Academic Network, is a great initiative by the Ministry of Education, Government of India, and aim to enhance the academic structure of India and building the connections among the global experts or students and educators. Through GIAN program at NIT Jalandhar, we are trying to engage brightest minds from all over the world with our students and faculty. So program enables the international experts to share their knowledge, collaborate in the research, and teach advanced courses that help our students to gain the valuable insights. So these programs provide our students the opportunity to interact with the global scholars and learning from their experience to enhance their academic and professional journeys. So moreover, through these programs, we look forward for the future collaborations at the international level and innovation at the international level in the various fields. So we appreciate here the special role of IIT Hyderabad for its valuable support to conduct the GIAN courses. Through India, the IIT Hyderabad very efficiently it is coordinating all the GIAN courses. So we are also thankful to Professor Murthy, National Coordinator GIAN and Director IIT Hyderabad, for promoting such courses in different institutes to facilitate strong networking among the international educators and Indian students. In current session, the total 11 courses with a budget of rupees 67 lakhs have been sanctioned for NIT Jalandhar only. So out of these, the 6 courses have been completed successfully, and experts from various countries like USA, Japan, Korea, Italy have been the part of this knowledge sharing program till now. So apart from this, that 4 more courses, apart from this course, of course, the 4 more courses will be conducted in the coming months. So we are grateful to our worthy director, sir, for his consistent support and motivation to organize such type of courses. So we are also thankful to our experts, course coordinators, faculty members, and participants for the successful execution of these courses. So during the entire program, I hope a comfortable stay of all the offline participants at NIT Jalandhar. On the behalf of the GIAN Committee NIT Jalandhar, I also welcome the suggestions and feedback of our participants to make such courses or programs better in the future. So with these words, I welcome you once again. Thank you. Thank you so much.
Thank you, sir. So now I would like to present a brief course report of our GIAN course, Information Theory and Mean Field Theory of High Dimensional Bayesian Inference, which is to be held in online mode at Dr. B.R. Ambedkar, National Institute of Technology, Jalandhar from 9th June to 13th June. This course presents an intersection of probability theory, machine learning, and statistical mechanics, which hold immense relevance in today's data-driven world, where high-dimensional models and uncertainty quantifications are fundamentals to solve real-world problems. I am happy to share that we have received 46 participations from various premier institutes like NIT Kurukshetra, Punjab Engineering College Chandigarh, IIIT Una, IIIT Allahabad, IIIT Bhopal, Bharatiya Vidyapeeth College of Engineering Pune, RV University, CMR University, Plaksha University, Lovely Professional University, DAV University Jalandhar, Jawaharlal Nehru, Government Engineering College Sundarnagar, Shulini University, Chandigarh University, Ghani Khan Chaudhary Institute of Technology West Bengal, IBM India, and we also are delighted to welcome our international participant, Dr. Giulio, which is a postdoc fellow at Sparse Tree in USA. I welcome all my participants. So now, may I request Professor GIAN Barbier, Associate Professor ICTP Italy, to kindly introduce and provide a brief course highlight regarding our course. May I take one moment to introduce Professor GIAN Barbier. Professor Barbier works at ICTP Italy, which is a UNESCO institute whose mission is not only to follow research excellence, but also teaching and scientific capacity building for developing nations. As a secondary affiliation, Professor Barbier also works at Theoretical and Scientific Data Science Group at CISA, Italy. Professor Barbier has been awarded a prestigious grant of 1.5 million euros from European Research Council to support his research in statistics and machine learning, along with many international distinctions and achievements published on his name. So with all this introduction, I welcome you, Professor GIAN Barbier, and may I request you to kindly share a course objectives with all of the participants. To you, sir.
Yes, thank you very much for the kind introduction. Do you hear me well? Can you hear?
Yes, sir, you are audible.
Perfect. All right. So first of all, would like to personally thank you very much, Jaspal, because thanks to you, this thing is happening. You're my direct contact with India, and so I wish to thank you. I would like to thank all the other organizers that I haven't had the chance to meet. I hope that next time there will be an occasion to meet physically. I'm kind of sad that I could not be here physically. This was the original plan, but given the course of the slight disturbances that happened these days in India, I could not come, unfortunately. But this is just a delayed visit. So concerning the course, so this course is a theory course, which is very much aligned with my own personal research. So the goal will be essentially to understand a number of concepts that are related to high dimensional inference. And the challenge for the students in this course will be that I will use both vocabulary, concepts, and techniques from very different fields that may look a bit disconnected, but I will try to show you that they are very much connected. I'm talking about information theory, statistical mechanics, and in particular a subfield of it which is called spin glasses, which is related with the study of disordered systems, and random matrix theory, which is the study of very large and random matrices. And what we are going to see is that by combining these tools and concepts in the proper way, we can answer very precise questions about when inference is possible or not. So this is the first question we're going to address, is given some data that will come in the form of a large array, a large matrix, which is made of signal and noise. Is it possible to extract the information? So this is really a question of information theoretic nature. The second question we're going to approach is it possible to extract this information, but in a reasonable time? So given not infinite time, given just a short amount of time, can we extract this information? So what I mean by that is using an efficient algorithm. This is more an engineering or algorithmic question, and we will see that sometimes the answer is different. So information theory will show us that information is extractable. However, there are what we call algorithmic hardness that arises and that prevents us to extract it in efficiently. And so the ultimate goal of the course will be to build a toolbox which will both conceptual and methodological, that will allow us to precisely define these limits of inference. And the final picture we will draw is what we call a phase diagram in physics, which will tell us when inference is possible or not, and when is it possible algorithmically or not. So this is the goal. So again, this will be a theory course, so it will be mostly about understanding important concepts, and I will show you also I will pick some specific methods in which we'll go more into the details. But really my goal is that at the end of the course you are able to take a paper from this field, which is a very interdisciplinary and broad field, very lively these days, and understand it by yourself. So that's the aim. I'm done, yeah. I can go in more details if needed, but you let me know.
Thank you. Thank you, Professor Jain. And I must mention and appreciate the efforts. It's 6 a.m. in Italy right now, and sir has kindly accepted our invitation to join the inauguration. Thank you, sir. Thank you. So if you may leave if it is required. We are just ending in 5 minutes. If it is possible, you can be online. Thank you. So I express a sincere gratitude to Professor Jain Barbier to kindly accept our course, and he will be taking most of the sessions in the due 5 days. Thank you, sir. Moving forward, I would like to invite Dean RC, Professor Rohit Mehra, to kindly address the audience. Sir, I request you.
Good morning to everyone, especially the participants who are present online and our subject expert, Professor Barbier, the director of the day, Professor GIAN Chakrabarti, my colleague, Dr. Sangal, Dr. Harsh Verma, Dr. Vijay, and Dr. Ashish Raman, the coordinators of the course, especially Madam Deepti and Madam Jaspal Kaur and other colleagues, and the participants who are present offline. So first of all, I would like to welcome all of you for such an informative topic which they have chosen, which is not aligned to a single field, but it is applicable to so many areas also. The reason is, like if you study the Bayesians or something else, because I'm basically a man of physics, so we are continuously applying these theories and these equations for solving many body problems also. And working upon these type of activities by organizing the GIAN courses like this. So I think the most of the benefit which our research scholar can pick out from these courses is the basic knowledge from the subject expert who are working in that particular area and they are master in their domain. And I hope during this tenure of 5 days, lot of deliberations will happen, lot of lectures will be delivered, and it will be beneficial for all the participants. And I think that you can apply this research or the knowledge to your areas and wherever you go and come out with some final outcomes. So thank you once again to the organizers. Thanks.
Thank you, sir. May I now request officiating director, Professor GIAN Chakrabarti, sir, to kindly address the audience. I request you, sir, to please address the audience.
Ian. Hello, good morning to all. I welcome Dr. Jean Barbier, the main expert of this GIAN course, Dr. Rohit Mehra, Dean RC, Madam Mamta, Dr. Sangal, Dr. Ashish Raman, Dr. Vijay Kumar, other faculty members and participants. It gives me immense pleasure to see that Department of Information Technology and Department of your Electronics and Communication Engineering are jointly hosting the GIAN program. This is your from your 9 to 13th of June 2025, and they have received 46 of participants. So I will ask the participants to remain attached with this program. Don't to neglect it. Get something at least to add some new, enrich your knowledge, you can say. And my all thanks are to the coordinators for conducting such a nice program. Have a good luck. Thank you.
Thank you, sir. Thank you for joining us, Professor GIAN Chakrabarti. May I now request Dr. Deepti Kakkar to present a vote of thanks. Respected Director, distinguished guests, esteemed academicians and faculty members, dear participants, it's my honor and privilege to extend vote of thanks on behalf of GIAN course organizing team. This movement marks not just the start of course, but also the beginning of meaningful exchange of ideas. First and foremost, I express my deepest gratitude to our Honorable Director, Professor Binod Kumar Kanodia, whose visionary leadership and unwavering support for academic excellence continue to inspire us. A sincere thanks to the Director of the Day, Professor GIAN Chakrabarti, for his guidance and unwavering support. I extend my sincere thanks to the international expert, Professor John Barbier, for agreeing to conduct this course and for bringing global perspective to our academic environment. I extend my heartfelt appreciation to our Dean R&C, Professor Rohit Mehra ji, for his constant support and guidance in ensuring the seamless execution of this course. A special note of thanks to Dean and Professor Mamta Khosla for gracing the occasion for her presence.
I express my sincere gratitude to Professor A.L. Sangal, Head of Department Computer Science, Dr. Ashish Raman, Head of Department Electronics and Communication Engineering, and Dr. Vijay Kumar, Head of Department Information Technology for their support. A special acknowledgement to the GIAN coordinator, Dr. Vimal Kumar Bhardwaj, for his contribution in making this event possible. A special thanks to Professor Harsh Kumar Verma, Mr. Bhupinder Jeet Singh, and all technical staff of Computer Center and NKN Hall for their support to make this event possible. Thanks to all the faculty members for gracing the occasion. Last but certainly not least, a huge thanks to our student volunteers, the most powerful task force behind this event. A special thanks to Dr. Jaspal Kauseni for your behind the scene work in organizing and managing the logistics of this particular course. As we are moving forward for the technical sessions, I am confident that this course will foster new collaborations and spark meaningful discussions. Once again, I extend my sincere gratitude to everyone who has contributed to this course success. Wishing you all a productive and enriching experience at GIAN course. Thank you so much. Jai Hind.
Thank you, ma'am. May I request everyone to kindly rise for the national anthem? Thank you, everyone. Now, may I request everyone to kindly join here for a group photograph. And all online participants may also switch on their camera. We will record you also in the group photograph. So, all please come here.
But I have to switch off the.
हाँ सिर्फ एक फोटो मुझे
अच्छा रहने दो
एक फोटो
ऑनलाइन वाले नहीं वाले
प्लीज ऑल ज्वाइन एक फोटोग्राफ आज ही अच्छी तेरी साझा पिज्जा
तो थोड़ा सा बैक ड्रॉप में रख दो तो ऐसे ऐसे आप मत करो
छोटी हाइट
नहीं छोटी चक्कर पर मैं हो जाता हूँ इसको भी
आप ही आ जाओ
बन जाओ ऐसे प्रोग्राम की आप ही आ जाओ वेरी गुड वेरी गुड
even the one it's talking which is important. Sir, Thank you, Professor Jen Barbier. So we are breaking for tea and thank you for joining. So to all participants, we will be having our first lecture at 11:40. Thank you everyone to join. So you may now leave. So we will be having our first session at 11:40. Thank you. I'm so sorry, we are having some delays of just 5 minutes because I have to start recording also. So I'm just logging into to one more device. Just give me 5 minutes and then we will start. Good morning, everyone. Am I audible?
Yes,
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 Dr. Jaspal, you're audible.
Okay,
yes.
thank you. Okay, I'm so sorry for the delay. Actually, my system. Thank you, Professor Jain Barbier, to just share the slides. So I will introduce some parts. Okay. Uh, Meantime, as soon as I get the laptop, I will on my video as well. Am I audible?
Yes.
Yes, ma'am.
Okay. Jaspal, do you hear me?
Hello.
Yes. Do you hear me?
Okay, so I will just introduce, then John Barbier will take up the session. Is it fine, sir?
Yes, yes. So it seems there is a
Okay.
trouble on your side, so I will do it. So let me not share these slides. I will do it on my
Yes, sir.
tablet then.
So I welcome everyone to the GIAN course, the very first lecture, Information Theory and Mean Field Theory of High Dimensional Bayesian Inference. Myself, Dr. Jaspal, and I will be taking up introducing, and then Professor Jan Barbier will take up the rest of the slides.
Just give me 1 second because I was not expecting to teach right now, so I was not ready. Excuse me. Okay. All right. Do the students hear me properly?
Yes.
Okay, great. So let me just ask if, some of you randomly, from one course to the other, I'm not asking each of you to do it for every lecture, could just, put on their camera, because to be honest, it's a bit difficult to teach in front of a black screen. I would find it a bit more nice for myself and probably for you also to show yourself some time, and this way it will be a bit more interactive. Of course, the next lecture, then you can disappear behind your camera, no problem, and I would ask some other students to show themselves if that's possible. At least I have the impression to talk with someone. Is that okay for everyone? Okay. Also, I would kindly request you to be a bit responsive when I'm asking questions. Otherwise, it will be very hard for me to gauge whether what I'm saying is clear, too fast, too simple. So just tell me as we move on. All right. So let me just say a few things. So I was not supposed to teach that lecture, so let me just put my thoughts. Let me structure my thoughts. Okay, so let me mention something. Do not stress too much about taking a lot of notes for that course, okay? In the sense that for me, it is important that you follow what I'm saying as it goes on, okay? Because I have written very detailed notes that will contain essentially everything I'm going to say, okay? And slightly more. So instead of trying to write down everything I'm saying while listening, I would recommend to just focus and ask questions live, and then I will send you the notes later in the day that will need to be slightly updated later, but at the end you will have a full document containing everything, okay? Perfect. So we're going to start with the main question, okay? So this course will contain concepts and techniques from different things, okay? The first one is, as the name says, it's information theory. Can you read properly? Okay, I will assume so. The second one will be statistical mechanics. So I assume this is a field where you're less familiar with, because if I understood correctly, most of you are not physicists. My background is theoretical physics. I moved to information theory and statistics later on, but we will see that it's very much connected, of course. And the third field toolbox we're going to use is random matrix theory. Okay. So I will give introductions, self-contained introductions to all of these fields, okay? And all that are going to be used to study inference problems in the language or in the framework, let's say, of Bayesian inference. So I'm pretty sure that most of you already have some knowledge about what Bayesian inference is, but I will recall some basic concepts. Okay, but first of all, what is the main goal of the course? Okay, the main goal will be to study one specific instance of a high-dimensional problem, because I will argue that even if we're going to focus on this specific model, most of the things we're going to say generalize to a very broad class of high-dimensional inference problems, okay? So do not imagine that what I'm going to say is very specific. That's rather the opposite. But I think that from the pedagogical point of view, it is important to fully solve, fully dissect one single model. And this is what we're going to do, especially that we have a finite amount of time. We have just 1 week. So I think it is better to focus on that single one. But you will be able to use all these techniques and ideas in a much broader context. So the model we're going to use, let me just quickly state it, is called the Spike-Wigner model, and this is a matrix inference problem where you measure y equal tau, which is a scalar, times a rank 1 matrix plus z. Okay, so think of y as some data. Tau is a so-called signal-to-noise ratio. This is a scalar. And x, which is a vector in Rn, is the piece of information we want to recover. So XX transpose is a matrix of rank equal to 1. And Z is the noise. Y is the data. And given this data, you wish to ask, so sorry, Jaspal, there are people that keep entering the room. Could you please take care of administrating this, because it's a bit difficult to teach while accepting all these people. Thank you very much. So the question we're going to ask is, given this data, are we able to reconstruct this rank 1 matrix? And we will see that it looks very special, this model, but it has tons of applications, and I will show you that later. Okay, but at the moment, let's just assume this model is interesting. So the first question that we're going to ask is really an information theory question, IT. Can the signal XX transpose, this rank 1 matrix, be recovered given the data Y? Okay? And by can here, I really mean we do not care about how costly it is for a computer. This is really an information theoretic question. Is there simply enough information in the data Y to say something meaningful about this rank 1 matrix? Okay? So this is the first question, and this is where really information theory and statistical mechanics will be important. And random matrix theory as well, we'll see. And the second question, which is more an algorithmic question, an engineering question, if you wish, is can it be recovered at low computational cost? That is efficiently. Okay, because it's very nice if you can prove that there is information in the data and therefore in theory you should be able to recover it. But if it takes the age of the universe for the best supercomputer on Earth to recover it, it's not a very useful result, right? The more useful result is one that says that indeed there is enough information, but also we can provide efficient algorithms that extract it in a reasonable amount of time. Okay, so we're going to study these two questions, but the first we need to study is whether it's possible, information theoretically. And then at the end of the course, I will show you how to extract this information in the best possible way and being efficient. And we will see a bit earlier in the course, actually tomorrow, how to do that with another algorithm, which is much simpler, but which is suboptimal. We will see. All right, so this was for the introduction. So let's now go to lecture 1, which is about Bayesian inference. Okay, so let me also mention right away that I will be a bit loose with the notations. I will not track what are matrices or vectors. I will say it orally, but you should be careful with this. The notations are well explained then in the notes. Again, you will have them later today, don't worry. You will be able to follow the notes in live. But if at some point you miss something, if the notation is not clear, just stop me. It's probably because I haven't defined it properly. Okay, I won't have time to be so precise with all the notation, otherwise we won't go through the course. So just stop me when something is not clear. So let me remind you the basics of Bayesian inference. Is y a parameterized function of x? So y is a function of x, yes, because you see this data there depends on x through this relation. So it's xx transpose plus z. So yes, y is a function of x. The data is a function of the signal. Thank you for the question.
So, do we want to estimate x as a value, or we want to estimate the functional form? I did not understand the
No.
problem.
This is a particular matrix. This is a matrix of numbers, and we want to evaluate these actual numbers. Okay, not just the functional form. We're going to assume that we know the functional form, in the sense that we know that y depends on x in this way, but we don't know what this noise is. We don't know the actual realization of this x, and we want to recover the xx. Okay?
Understood. Thank you, sir.
Thank you. Perfect. So in Bayesian inference, we have three main ingredients. The first is the prior, P of x. So I will always use the notation x for the unknown parameters, the information to recover. Y will be used for the data. Okay. So the prior represents any a priori information you may have about the signal before observing the data. Okay. The second ingredient is the likelihood. So the likelihood is the probability distribution of observing some data y given x. Let me mention here that what I'm saying is not specific to the model I defined before. What I'm saying now is completely general. Okay, y and x can be anything. Okay, they don't have to have the same dimension. X can be a tensor, it can be anything, y can be anything. Okay, this is completely general. So the likelihood is the probability distribution. It's a conditional distribution that models the data generating process. It is your model of how the data y was generated if the unknown parameters were taking the value x. Okay? And from these two ingredients, you can construct the main object of interest in Bayesian inference, which is the posterior distribution. So the posterior distribution is the law of x given y, which is given by Bayes' law as the product of the prior times the likelihood divided by the normalization. And this normalization, of course, you can write this as the joint law of x and y. This is the product rule. Okay, this is by definition of what the conditional distribution is. And so if you are integrating the joint law of x and y with respect to x, this normalization is just P of y. That we call the evidence. This is the evidence in the Bayesian language. Okay? So I'm sure that these are known things. So let's move on. Let me evaluate the time. Jaspal, can you tell me until what time can I teach? Can I take slightly more than what was expected, given that we started later? I will assume so.
Am I audible?
Yes.
Sir, we have half an hour more. We can, because we started late, so we can cover maybe 30-40 minutes more. What all we have planned for lecture 1, we can cover.
Yes, this will be a bit difficult to finish in half an hour, but okay, let me...
We can take 40 minutes, what all you require, we can take.
Okay. So maybe what I can do is maybe just open the notes I've written and go through them with you. Yes, because otherwise I think it will be too long. So
yes, I shared slides with you, so maybe you can we can cover from that.
But I will simply so because otherwise we won't be on time given the delay.
Yes.
So let me give me 1 second. Yes. Excuse me, everyone. This is it seems to be a constant in the scientific world. Every first lecture, there are problems. This is unavoidable, but we should be okay. Perfect. So do you see the notes? So basically, these are the notes I'm going to share with you. So let's try something. I will go through the note. Don't read all the sentences. Just focus on what I'm showing. Okay. And let's see if the pace is slow enough so that you can follow. If you cannot follow, please stop me. I will say much less things and I will just give you the note later on. And all right, so that was the motivation. Okay. This is not, I don't like the way it's shared. Excuse me. I will, okay, that will leave. Okay, so that was the model, right? So let's go to where we were. Maybe it will be actually easier because the notations will be more clear. So we are here. So the Bayesian posterior is the following. This is the law of the unknown parameters x given the data y. And as I said, it is the product of the likelihood distribution times the prior, which is then correctly normalized. And this normalization is called the evidence. Okay, so this is very simple, basic problem. So let's consider one example. Here, example 2. Let's say that you have you are a statistician trying to evaluate the distribution of the heights of people in a population. Okay, so what you could do is assume, let's say from statistics from other countries, what is the typical height of people, okay, in the world, let's say, for, let's say, males of a certain age, and what is the standard deviation of this height, okay? And so you will have some prior given by the statistics, which is that the expected height of a human in the world is 1.70 meters. The standard deviation, sorry, the variance of it is 25. And so your prior is a Gaussian distribution with this mean and this variance. Then you would sample the distribution to get some data specific to your country, India. And you would realize that the empirical average, the average you compute over these samples, is actually bigger. It would be this mu bar, which is 175, obtained from, let's say, 10 samples. And the variance you would observe is bigger than the one you assumed in your prior. It would be 49 centimeters. So this is your data, okay? And Bayes' theorem tells you how to combine your prior and the data. And if you do the computation correctly, you realize that the random variable corresponding to the height given now the data, so you are updating your knowledge about this random variable by combining your prior and the data, you would obtain some formula here, which I won't explain. This is very simple, actually. This is an exercise to try. And you would realize that the posterior distribution of this height is now updated, and the mean is not anymore the prior one, is not anymore 170. It's closer to what you observed in the population. It's 174, and the variance would be, I think there is a typo here, it's 41, okay, and not 4.1. So you have updated your belief in a principled way, and now you have a better, more reliable description of the distribution of the height in the population. Okay, so very simple example. So this notation means the random variable corresponding to the unknown, in this case the height, conditional on having observed the data y. Okay. Bold variables will be used for vectors and matrices, while without bold, normal letters will be for scalar random variables. Okay. Perfect. So now that we have a tool, a way to obtain probability distribution of random variables which combine our prior information, our prior knowledge, together with data. This is the posterior distribution given by Bayes' rule. A meaningful question is how to use this probability distribution to take a decision. So making a decision means estimating, choosing a value for the unknown parameters. Now we have a distribution. How do you pick the value for this unknown parameter? So this is done using what we call Bayesian decision theory, which goes as follows. So the first main ingredient in Bayesian decision theory is a notion of goodness. So how to quantify whether a decision is good or not. And this is done thanks to the so-called loss function, which depends on the unknown parameters x and on your decision. Think of this delta as an estimator for the unknown parameters x. Okay, so this function is the cost of choosing the decision delta when the true parameters is x. But of course, the problem is that you do not know x. Okay, that's the whole point. You are trying to estimate x. Okay, so you do not have access to the loss function defined in this way. Okay, because this x is unknown. Okay, so the way to define a meaningful question that you can actually compute from the data is the so-called risk. The risk is the expectation of the loss given the data. Okay, so you see now the risk, which becomes a function of your decision and of y, not anymore of x, of y, and y you have it in your hand. It's the data. So you can compute a function of this form. This is meaningful. It only depends on things that you can control, the data and your decision. And by definition, the risk is the expectation with respect to the posterior distribution of the unknown parameters given the data of the loss. Okay, so you are averaging the loss with respect to the unknown parameters using your best guess of what the distribution of these unknown parameters is, which is of course the Bayesian posterior distribution. Okay, so now we have a meaningful quantity that we compute. This is the risk, which is the average loss, the posterior average loss. Okay, and what we call an optimal decision. Okay, an optimal decision is given by definition as the minimizer of the risk. Okay, so
Optimal decision.
yes, was there a question?
No, I was getting sorry for interruption.
No problem, no problem. So again, I repeat, everyone, you can stop me whenever you want. By the way, I think that I will do like this and follow the notes because otherwise I won't make it on time. It's a bit difficult to write on the iPad. At the Blackboard, it's a bit easier. Is the pace okay? Are you able to follow when I speak like this on the notes?
It's a bit fast, but we can grab.
It's a bit fast. So I will slightly slow down. Okay. Thank you. So now that we have this risk function, which quantifies how good a decision, which means an estimator for the unknown parameters, is, and that depends on our observed data, so it's something we can compute. The optimal choice is, of course, the one that minimizes this risk. And this is what we call a Bayesian optimal decision, okay? And we denote it by this delta star. The star here would mean optimal. And this is only a function of the data, as it should, because it's the only thing that you have in your hands, the only thing you can observe, okay? So let's look at an example. If we take for a loss the L2 distance, so the Euclidean distance between the unknown parameters that, let's say it's a vector, between the vector of parameters and our estimator of it, delta, what is the optimal decision one can take? So let's just use the definition and compute. So I take my loss here, and I'm averaging this loss with respect to the posterior distribution. This is what this notation means here, okay? So this notation, expectation of something conditional on y, really is the same notation as the expectation with respect to x given y which is really an integration with respect to x of p of x given y of the something. Okay, so this is an expectation with respect to the posterior. Okay, so here, this notation is here to remind us that we're conditioning on the data. So it means the data is given to you, and therefore we are talking about the posterior distribution. Okay, so I'm computing the average of my loss, my Euclidean distance in this case, with respect to the posterior distribution. So I can just do very simple manipulations here. I can develop my square here, and I obtain three terms. The first term comes from the norm of x, which does not depend on my decision. So this is just a constant. I can forget this term. This is a constant with respect to delta, which is the object I want to focus on right now. The two terms that depend on delta are here. Okay, we have the norm squared of delta, and the inner product, this point here means the standard inner product, between my delta and what appears to be the posterior mean. Okay, so this notation there is the mean of my unknown parameters with respect to the posterior distribution. Okay. Okay, and I can solve this equation. So this loss, by the way, this is an Euclidean distance, this is a square, so it's like a parabola. It's a convex function. So if I'm looking for the minimum, a convex function has a unique minimum. So I can just look for the decision that minimizes this convex function by looking at where the gradient cancels. Okay? So I'm taking the gradient of what I just wrote with respect to my decision, which is a vector equal to 0. And what you obtain is this equation there. Very simple. And you solve it, of course, and it gives trivially the following. So the optimal decision when you consider the Euclidean distance as your notion of loss, as your loss function, is the posterior mean. Okay? So this is what we call the Bayes estimator. Okay? So it tells us that when we consider Euclidean distance as a notion of how good an estimator is for a given unknown, we are trying to minimize the Euclidean distance between the two. Given only the data, the best we can do, the very best we can do, is to compute the expectation, the mean of the posterior distribution. Okay? This is the Bayes optimal estimator. Let's consider, so we call it also the minimum mean squared estimator, or MMSE estimator. Simply because this Euclidean distance is also called the mean square error. Okay? And we are minimizing the mean square error. Okay, so this is the best possible estimator in this sense. So let's consider another example. Let's now take the loss to be the so-called 0-1 loss. So it's a loss which is 1 if your estimator is not exactly equal to the unknown, and it's 0 otherwise. Okay? So you are forcing your estimator, you're only happy when you recover exactly the unknowns. So this is a meaningful loss only in the case where these unknowns are discrete. Otherwise, you cannot reconstruct perfectly real valued numbers. Only discrete numbers can be reconstructed perfectly. So for discrete random vectors, let's say, we can consider this loss. And we do the same exercise. We compute the risk associated with it, which is the expected loss. And what you get is simply 1 minus the probability distribution of a given decision with respect to the posterior distribution. So you can try, maybe you don't see it right now, but this is very simple. You plug this definition of loss, where this 1 is the indicator function. It's 1 only if this event is verified there. and it's 0 otherwise. Okay? So you plug this here and you will realize that what I have written here is correct. And in this case, how do you minimize this risk? You see, you want to, because there is a minus here, you want to maximize this probability, okay, in order to minimize this risk. And therefore, the Bayes optimal estimator in this case is, so what's the best decision you can do is to maximize the posterior distribution, is to take the argument that maximize the posterior distribution, the argmax. And we call this the maximum a posteriori estimator for obvious reason, okay? I hope this was clear. So this was a short introduction to Bayesian decision theory. So now we have essentially a framework to understand how to pick an optimal decision, how to pick an optimal estimator for unknown parameters when we are able to write down the posterior distribution according to Bayes' rule. Okay? Perfect. So, again, do not read everything that appears at the screen, just focus on what I'm pointing at you, okay? So now the question is, why is the Bayesian framework important, especially when we go towards high dimensions? And remember that this course is really about inference in very high dimension. We're not interested in reconstructing unknowns, which are, let's say, just scalars or 2 or 3 numbers, okay? This is the statistics from the past. So classical statistics from the 19th century and for the past 100 years, people were interested in settings where basically you have lots of data and you are trying to infer few unknowns. So, for example, you could do experiments. You were Newton and you are throwing some balls and you are recording the trajectories of the balls, and the unknown parameter you want to infer is the gravitational constant. This is just one number and you can measure tons and tons of trajectories. So this is classical statistics. Lots of data and few unknowns. This is not what we are interested in this course. What we want to study is high dimensional inference. The difference is that you still have lots of data, but you as well have lots of unknown parameters, and their numbers is essentially comparable, okay? And this is where really new phenomena and interesting things that we're going to see happen. This is what we call high dimensions, okay? So again, if I denote by X the unknowns and Y the data, let's think of them as vectors at the moment, the dimension of the unknown, P, is proportional to or much greater than the number of data N. Okay? So this is really the high dimensional world. Okay? And when you are in high dimension, in particular, the tools from classical statistics, what people were using in the 19th century, they fail. And one of these tools is called maximum likelihood estimation. Okay, this is the weapon of choice to use if you are in the classical regime. The classical regime, contrary to this, means the number of unknowns is much smaller than the number of data. So this is the classical statistics. Okay. When you are doing classical statistics, you can show that actually the best to do to make a decision to estimate the X is maximum likelihood estimation. What does it mean? It means to choose X MLE. So this is our optimal decision. When we have lots of data, you can show this. This is the maximizer of the likelihood, okay? So you do not need any prior. You can just take the likelihood, which is the conditional law of the data given the unknowns, and maximize it. You see, this is different from the maximum a posteriori estimator that I defined just above. The maximum a posteriori estimator includes your prior information, which is very important when you are in high dimensions, because I will explain now, but in high dimensions, you need prior information to make inference. Instead, in low dimensions, so in the sense of classical statistics, lots of data compared to few parameters, just using the maximum likelihood estimator is optimal, okay? But this is not the case anymore in high dimension. In particular, if you take this kind of decisions in high dimension, you will induce overfitting. You will tend to essentially reconstruct things that are related to the noise rather than the signal, okay? Okay. Perfect. So let me see where we are time-wise.
Professor, if you wish to, we can cover curves of dimensionality in the next lecture after lunch. It is as per your choice.
Yeah, I mean, I need to say quite a few things after lunch as well, but this, if...
okay, you can take maybe, if you wanted to cover, we can cover.
Maybe I can take 7 minutes. I won't need more. Okay. So let me discuss a very important notion, which is the curse of dimensionality. The curse of dimensionality is precisely the reason, let's say the concept behind, let's say a set of phenomena that imply that classical statistics tools, such as maximum likelihood estimation, fail when you go in high dimensions, okay? You need to rethink statistics when you go to high dimension. And the reason is a set of phenomena, actually, that we put in a bag, a conceptual bag that we call the curse of dimensionality. So it can mean many different things, and I will just show you a few of these phenomena that basically say that when you go towards high dimensional spaces, making inferences in high dimensional spaces, everything changes compared to the low dimensional world where you evaluate low dimensional quantities, like the gravitational constant, just one number. What happens when you evaluate very high dimensional vectors? Everything changes. This is what we mean by the curse of dimensionality, okay? So, in particular, when you go towards high dimension, one of the key problems is that you can never fill the data space. So what do I mean by this? What I mean by this is the following. Imagine that you are trying to evaluate just a real number. So the true parameter is this value there in blue, okay? And what you are measuring are, let's say, noisy observations of this true value, okay? So this noisy observation, this data, are points that are somewhere there, okay? Some are far, many are a bit close to this point, okay? So you see that basically the more I give you data, the more I fill this space, okay? And let's assume that this space is just 0, 1. Okay? You see that if I want to be sure, let's assume that these points are sampled in a manner, and I want to be sure that I have enough points to be close enough to the truth, like this, with a certain precision. You see that the precision that I get, this delta x, let's say, between 2 points, the typical distance between 2 of my points, goes as 1 over the number of data. So I can quickly fill the space somehow. It means that distances between points, between data points, tend to go to 0 as the inverse of the number of data. okay, in 1D. But now, if you go to 2D, 3D, 4D, 100 dimensions, you need more and more and more data because you are not filling just anymore a line. You are filling a hypercube, if you want. So very high dimensional space. So imagine that you want a precision, a resolution, meaning that you want that the typical distance delta x between two points in your space. Let's assume we sample the points uniformly, just to simplify, okay? We're sampling the points uniformly. We want the resolution to be 10 minus 2. In one-dimensional space, the number of points you will need to have such a resolution is 100, okay? Because if you put 100 uniform points on a line between 0 and 1, the typical distance between them will be 1 over 100. But now if you want to have the same resolution in the sense of having points which are that close to each other in this space, when the number of dimension is now 10, 100, sorry, so high dimension, even if it's not so high, will be 100 to the 10, which is 10 to the 20. So you see, you need exponentially many more points to fill the space, okay? But of course, you never have access to that many points, okay? So what does it mean, these very simple examples of filling points uniformly in a space? It means that in high dimensions, if your unknown parameters live in high dimensions, you will never have data which are close to each other's in this. You will never have, like, think of this data as kind of noisy observations of these unknown parameters. These noisy observations will typically be very scarce, very sparse in this space. They will not fill the space properly. Even if you have 10 million or 10 to the 6, which seems to be a big number, data, this is really vanishingly small compared to what you would need to have such a small resolution. So in high dimension, you always need so much points to fill the space that you never happens, okay? So this is what we call the exponential sample requirement. So data in high dimension is very sparse and points are very far apart, okay? Another property of high dimensional spaces is the dominance of boundaries. So this is another weird property in high dimension, which can be exemplified by the simple formula. If you take a d-dimensional sphere, okay, so you just take the formula of a sphere in d dimension, and you compare the volume of a shell which is at the boundary. So this is the volume of the shell between r minus epsilon and r for a small epsilon. You compare that to the total volume of the sphere, and you see that it goes to 1 if the dimension goes to infinity with this formula. So this is a very simple exercise. You should show it. This is just volumes of sphere. So what does it mean? It means that if you put any point at the center of a ball in a high dimensional space, most of the volume, most of the points can only lie very close to the boundary of the ball. Okay, they cannot fill the space in the middle because most of the volume is actually contained very far away from the center. Okay, so the picture that you have in mind of a ball in 3D is very wrong in high dimension. In high dimension, the ball does not look like a ball like you imagine. It's a very weird object where most of the volume is contained close to the boundary of the center. Okay, it's really compressed at the boundary. And so this in particular implies that every points in high dimension are very far away from each others. Okay, so it implies in particular that naive algorithms will fail in high dimensions. So let's people are still joining. So let's consider the following classification problem. Assume that the space is again the hypercube 0, 1 to the d, and you have 1000 data points, which are sampled uniformly in the space, okay? And the classification problem is the following. The label associated with a point, if you want the color of a point, every point in this hypercube can take one of two colors. It is 1, meaning white, if the sum of its components is greater than the dimension over 2, and it is 0, meaning black, otherwise. So we have these black and white points in this very high dimensional space. And this is our data. And now, of course, you do not know this rule. The inference problem or the learning problem, here this is the same, is to understand what this rule is given the data only, given the observations of these black and white points, okay? And the naive algorithm that works very well when you are in low dimension, but fails when you are in high dimension is the following. It's called one nearest neighbor algorithm. This is an instance of the GIAN algorithm in general, the K nearest neighbor algorithm. So what you do is very simple. So imagine that now you have a new point, the color of which you do not know. So you want to guess whether this point should be classified as black or white, given the observations of many black and white points, 1000 of them. So what you could do, because again, this rule is unknown, is the following, is just to pick the nearest neighbor of these points of unknown class and say that the class for this unknown should be the one corresponding to its nearest neighbor. Okay, it's a very simple classification rule. But if you do so, it will quickly fail as you increase the number of dimensions. If you go from d equal 2 to 200 to 2000, it will fail. Why? Because you can compute, you can just do a simple simulations, you will realize that the mean, the average distance between any 2 points in this space, like grows as the dimension grow, okay? But at the same time, the nearest neighbor of any point distance also grows. So basically, you can take any point in this space, there are many other points, and you compute the average point with respect to them, and you can also compare that to the distance with the nearest neighbor. And you see that these two distances in low dimension, they are very different when d is equal to 2, but in high dimension, they are very close to each other. What does it mean? It means that there is no more notion of local neighborhood. It makes no sense to compare a point to its closest neighbor because it is essentially at the same distance than any other points, okay? This is again related to the fact that if you think of this unknown point at the center of a ball, all the remaining volume is at the boundary of a sphere around it, okay? Of this high dimensional sphere. And so it makes no sense to make decisions based on notions of distances, because notion of distance loses meaning in high dimension. Okay? Does it make sense what I'm saying?
Yes.
Okay. Thank you for being present, by the way. I don't know your name, but I'm happy to see your face.
Arpita.
Nice
My
to
name
meet
is
you.
Arpita. Same here.
All right. So like I said, in high dimension, distances become uninformative, and many naive algorithms are based in low dimension on comparing distances. So you cannot do that anymore in high dimension. The data concentrates in boundary regions. Remember these examples of the sphere. And notions of local neighborhoods disappear. There is no more neighborhood. In high dimension, every point is extremely far away from any other point. And this is a big problem. This is the curse of dimensionality, okay? So the way to fight against the curse of dimensionality is by making assumptions. And this is why Bayesian inference becomes so important. Okay? Bayesian inference is about combining the data with assumptions in order to make better inferences. And assumptions in high dimension become absolutely crucial because of the curse of dimensionality. So there are different types of assumptions you can make, and there are tons of techniques to do different type of assumptions. So one thing you can do always, which is a sort of assumption, which is dimensionality reduction. You can say, okay, it's too difficult to work in high dimensional spaces because points have no neighborhood, distances make no sense. What I can do is to reduce the dimensionality. I can project back my high dimensional data to low dimension, and this is done through different techniques. One is called principal component analysis, and we're going to study it in detail. This is very much related to this course. But here you're making an assumption somehow. So it's a Bayesian procedure as well, because you're making the assumption that there exists a meaningful subspace of this high dimensional space on which I can project my high dimensional data without losing all the information. Okay? So there is some specific low dimensional projections that make sense to consider, which is a prior. Because what is this low dimensional subspace? You're making an assumption that it exists and you can find it, and the way you find it is somehow can be thought as a prior in the Bayesian context. Another thing you can do is called feature selection. Okay, so feature selection is about saying, okay, my data lives in very high dimension, but probably many of its, let's think of this as a vector. My data are samples of a vector. Many of its components should not matter too much, should not be very relevant for the task, for my inference task. So maybe I can somehow just select what are the features, what are the components of my vector that do matter to make inference. It's again a type of dimensionality reduction. You're reducing the dimension, and you can do that based on different techniques, based on in particular, what we call the lasso, which is a prior that says that basically most components do not matter and can be set to zero. Like if you have data living in high dimensions, what you do is to say all the components that are sufficiently close to zero, I just set them to zero. Okay, and the only relevant ones are the non-zero ones. And so doing so, you can shrink the dimension of your vector and make the inference easier. Okay, and you can use regularization. Regularization is another type of prior. For example, you can assume that the unknown parameters have a norm which cannot be too high. So this kind of things. Okay. So all these techniques can be seen as different forms of priors in the Bayesian language. Okay. All right. So let me stop there. And we're going to continue a bit later by introducing the basics of information theory.
Sir, I have a quick question.
Yes, please go ahead.
On the distance part, like when you mentioned that the mean distance grows as dimensional to decreases, this was the intuitive part for me, because I thought that sampling algorithm prefers faraway things, but when we went to the mean nearest neighbor distance, this was the less intuitive part for me. That even the nearest neighbors, because even in high dimensional spaces, we could sample just one distance away thing. So why is the mean nearest neighbor distance increasing as dimensionality increases? This is something I'm not able to wrap my head around.
Okay, so the sound quality was not really good. So let me see if I understood. Your question is essentially is why is this mean distance between points increasing with the dimension? And why is this?
Yeah, I'm sorry for the sound. What I wanted to say was the main distance. I think this increases because of the sampling thing, because most of the points are at boundaries. Then we're anyway sampling points far away. But the main real is neighbor distance thing. This is something that is very non-intuitive for me.
Yes. Okay.
Like, why is it increasing?
Yes. So your question is, so the mean distance is increasing with the dimension, but why is that so that also the typical smallest distance between points increase with the dimension, right?
Yes, sir.
So, yes. So imagine again consider again this formula. This formula is telling us that if you take a ball in high dimension, most of the volume is close to the boundary. So imagine that now you are sampling, so you place yourself
Yes,
at the
sir.
center of such a ball, and you are sampling random points in this ball, okay? Let's say 1,000. Because quasi all the volume is contained at the boundary, it means that almost all these 1,000 points will be close to the boundary. You have because the chance to be anywhere in this ball is proportional to the volume of this subvolume, right? So you have a full ball and you take a small subset of this ball. What is the chance to sample a point here? It is related to the volume of this ball divided by the total volume, right? But
Yes, sir.
the total volume inside the ball is going to zero in high dimension because all the volume is dominated by the boundary. So it means that if you sample points uniformly, randomly in this ball, the chance to fall close to the center is going to zero with the dimension because there is no volume. And in particular, the closest point will be far away. Yes.
So wouldn't there always be a point? Let's say I have an n-dimensional vector. I can just perturb one dimension of it just by one and find the closest neighbor at one in each of the dimension.
I'm sorry, I do not hear well enough your question. I don't know if it comes from my side or if the others hear you properly. But
maybe you can write the question in the chat. That would help. Your voice is breaking.
I understood, ma'am. Yes, ma'am. I will write it up in chat. Thank you, ma'am.
Okay, if the question was not properly answered, please send it in the chat and I will try to answer, okay? All right, so are there any other questions by the others?
Hello, very good afternoon, sir.
Hello.
Am I audible?
Yes, you are.
Okay, so my question is like what you told about D-sphere, for example, and if my question is if there is a zero from zero dimension to the infinite or the d dimension hypercube or whatever it is, like in a matrix, it is for hypothetically, like if we start with a zero dimension point data set to the 1,000, 2,000 and to the infinity, then does it is it like comparable for the each data sets will be comparable for the same distance concentration function or and boundary dominance?
No, of course no. So what I said here was specific, somehow specific to the the simplest setting where you just assume that points that we call the data points are sampled uniformly at random in high dimension, okay? But of course, in reality, for real data sets, points are not sampled uniformly. If you consider, I don't know, if your data set is made of images of dogs, these are very structured data, right? So these are not uniform points. So you can think of an image of a dog as a vector where every component indicates the value of a pixel, let's say black and white, okay, to simplify. So this is a very high dimensional vector. And of course, the pictures, like if you think of all the possible pictures of dogs, they do not fill uniformly the 0, 1D space. So let's say D, here is the number of pixels. And of course, the set of images of dogs is not filling this space, okay? It lives on what we call a lower dimensional manifold. It is a subspace of 0, 1 to the D, okay? But it's still a high dimensional space in itself, okay? But so it means two things. It means that this curse of dimensionality is there if you make no assumption about the data. So if you know nothing about the data, the best you can assume is that it is sampled uniquely in the space. And therefore, you have this issue of the curse of dimensionality. But now, if you assume something about the data, in particular that it lives on a smaller subset of the whole space, it's called the lower dimensional manifold, then maybe you can make inference and learning easier. And this is what machine learning algorithms and Bayesian algorithms do. They somehow try to learn to understand what is this lower dimensional subspace that matter, okay? So in the Bayesian language, if you assume that your data is structured, you could do this. You could assume that it is not true that all the values of all the pixels matter and can take any value. This is not the case for images of dogs, for example. So somehow they should be a better representation for the data. They should be a lower space in which the data lives. It does not fill the space completely. And this is what we are trying to learn when we do, excuse me, where did I mention this? Yes, so techniques of dimensionality reduction. Oops, what is happening? Techniques of dimensionality reduction or feature selection, they're trying precisely to encode this prior information in the model that the data should not fill the space uniformly, that it should live in a subpart of the space. But then you need to learn what this space is. But simply the fact of assuming that there is such a lower dimensional space will help you to make inference. So this is a prior, a very important prior. But nevertheless, so what I'm saying is that you can fight against the curse of dimensionality by making prior assumptions, such as the fact that the data is structured in a certain way. Does it answer your question?
Yeah, okay, sir. Thank you.
Okay. So may I request everyone to kindly switch on their camera? We will take one screenshot for this lecture. So may I request everyone who are there, may please online, may please switch on their camera. Am I audible?
Yes.
Yes, okay. So we will take one screenshot and then we will break and then we will have another lecture at around 2:40, maybe 10 minutes later, as Professor Barbier says. Sir, what time we have to rejoin at?
We rejoin whenever you want, Jasper.
Okay, 2:40 as planned.
As planned.
Or if you want to delay, we can delay 15 minutes because this lecture has extended already half an hour.
No, but 2:40 it means almost in an hour and a half. That's more than enough.
That's more than enough. Okay, so we will go as per scheduled time. That is 2:40 p.m. after lunch. So may I request everyone to kindly switch on their camera. We will take one screenshot and then we will leave this session.
So we stop sharing. Let me stop sharing.
Okay, yes, now we can see everyone.
Perfect.
Yes, perfect. So maybe we take some screenshots.
GIAN course. GIAN course है ना?
Okay,
All right.
thank you. I thank everyone to join. So maybe we all will rejoin at 2:40 p.m. now. Thank you everyone to join, and I thank Professor Barbier to share time. Thank you.
So just one comment. There is Moti who asked his question on the chat. Can I?
Oh yes, there is one more question on the chat. Yes, should I read?
Yeah, maybe I can just read a part. So the question is, if we change an n-dimensional vector by just changing one component, we will have a nearest neighbor at an arbitrarily small distance. Okay, and indeed, if you take your vector in high dimension and you just change one component, you will have another point which is very close, right? This is true, Moti, but the fact that you should imagine that these points are kind of sampled. What I was saying was true when you sample these points uniformly. So the probability that you change only one component by a small amount is extremely small, right? It's exponentially small in the dimension. So the event that you're talking about here will never happen. Of course, in real data, points again are not sampled uniformly in the space. You have structure, but at the same time, you always have noise, right? So you have some level of corruptions, and in high dimension, even a small amount of noise can separate a lot any 2 points. So what I was saying remains true even if the data is structured due to noise. Okay, it never happens that you sample a point which is very close to one by just changing one component. Okay.
Thank you, sir.
You're welcome. So see you for the next lecture on information theory. Bye.
Okay, thank you. Thank you everyone. So when we disconnect, we will join at 2:40, in 1.5 hour. After 1.5 hour. Chalo.
Hello, welcome back, everyone.
Hello, sir. Thank you. Sir, just give me 5 minutes. I will start recording also.
So while Jaspal is setting things up, let me send on the chat a link to an overleaf document, which is the one I'm sharing right now on my screen, and this is the notes that you can have access to, and which contains essentially all the material of this course and a bit more. Okay, I sent it on the chat. So if you click there, you should be able to access the document. Let me tell you right now that the document is not finished completely yet. I still need to add the lectures for the last day and to polish the one for the 2 last days, let's say. But most of the material for the 3 first days, at least, is clean. So it's only 12 of you. I don't know if it's normal.
Yes, sir, you may proceed. I have started the recording as well.
Yes, Jaspal, I see only 12 people. Is that normal?
No, I think we can wait, sir. The time was 2:40. We are still having 5 minutes to start. So let us wait for 5 minutes and then we may start.
No, it was not 2:30.
It was 2:40, 4040.
Okay, perfect.
Hi,
Hello. Where are you located, by curiosity?
I am in Bhopal, Triple IT Bhopal.
Okay. What's your background?
I have worked on reasoning with uncertainty, and I'm trying to deploy this Bayesian theorem for trust and recommendation system. So I wanted some proper momentum in it. So that's why it is quite helpful. My supervisor suggested me to attend the lecture. And
Okay.
he said that the first lecture will help you a lot.
Jasper, I will be waiting for your green light. Huh? I don't know when you want me to start.
Sorry?
No, I'm talking to the organizer. I'm just asking her when should I start.
Okay.
लाइव वेबकास्ट टाइम से किया हुआ तो भी स्टार्ट रहता है क्योंकि लाइव वेबकास्ट जाना था ना यूट्यूब
I'm sharing.
yes we can start
I don't say anything.
yes sir we can start
Okay. So I see only 15 students. I don't know if this is normal, but okay. Okay. So Jasper, I will let you accept the people in the waiting room. Okay. Perfect. Okay. Can I remove this sound? Okay. Okay. So I see more people now. So let me just say again that I've sent on the chat, as you can check, a link to an overleaf document, which is basically this document. Okay, so you have all the notes accessible, and so this hopefully should help you. Let me mention that they are not finished, so the especially towards the end of the document is incomplete. So you can already use the document for at least the 3 first days, where the lectures are mostly complete, the document as well. But I will update this document during the week, so do not hesitate to check it again at the end of the week to get the updated document. Okay? Perfect. So let's start again. So just with this new way of proceeding, in the sense that I will go through the document like this, let's just, in order for you to be able to focus of what I'm actually saying, while I'm talking about some part, I will emphasize it like this or like this. So do not try to read all the page. These are not slides. I'm really working on the document. So don't try to read everything. Just listen to what I'm saying and just focus on the definitions that I'm emphasizing at a given moment. Okay? Perfect. So let's just recap quickly what we did this morning. We introduced Bayesian inference, okay, which is a framework to perform statistical inference combining data, which is modeled through the likelihood distribution, together with prior information we may have about the unknown parameters to infer. And this is done through the prior. We combine the two through the post-error distribution, and then we have this probability distribution, which we need to use somehow to make inference, so to get really an estimator for the unknown parameters. This is what inference is estimation. And so what we've seen is that there is a formalization of how to make optimal decisions from the Bayesian perspective. This is called Bayesian decision theory. And what we've seen is that first we need to define a notion of loss, right? I cannot remove. A notion of loss. You remember loss function, which defines our notion of distance, of discrepancy between the true parameters and our estimator, our decision, delta, and the true parameters x. And unfortunately, this loss cannot be computed because it depends on the unknowns, but we can define the risk, which is the average with respect to our best guess of what the probability distribution of the unknowns are given the data, which is the post-error distribution. So from there, we defined the risk, okay, which is the average of the loss with respect to the post-error distribution, right? And once we have this risk, we were able to now give a sense of what is an optimal estimator, an optimal decision. This delta star, that depends on the data only, is the minimizer of the risk for a given loss, okay? And this is computable because it only depends on the data which we observed, which we have. It does not depend anymore on the unknowns that we're trying to infer, okay? Because we averaged over it here. Perfect. So we have this this notion of optimal estimator, which is related to the post-error distribution. The question now is to study these optimal estimators, is to try to get to quantify the performance of such an estimator, okay? And what we are going to see in this lecture is that one way to quantify the optimal performance one can aim for is to go through a notion of that quantifies the amount of information contained in the data. It's called the mutual information, and this is deeply related to the Shannon entropy. These are basically the fundamental objects in information theory, and we're going to introduce them in this lecture. So now we introduce this notion of quantification of information content in the data about the signal. And we will see at the end of the lecture that if we can access this information content, you can compute directly the performance of Bayesian optimal estimators. Okay, so this is really the goal. We're going to connect information to performance of optimal estimation, right? So like the first lecture, if some of you are not shy and would be kind enough to show their faces, it would be really great for me. I would be very happy if you wish to to be present with me in the room so that I don't have the impression to talk to just a computer. No one is wishes to show themselves. Thanks a lot, sir. Nice to meet you. What's your name?
My name is Moti Rizal, sir.
Nice to meet you.
Thank you, sir. Nice to meet you too.
All right, thanks a lot. That's very, 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 very nice to see real faces. All right, let's go in this new topic. So information theory. I'm going to assume essentially almost no knowledge, so bear with me. Hopefully it should be simple enough to be understandable in a self-contained manner. I'm going to not be fully formal. My focus really is for you to understand the concepts, okay, rather than all details of every equations. This is impossible for this kind of courses. Then when you want to go to the details, you have references, you have more details in the notes. But what is important to understand is what the notions I'm going to discuss mean, okay? And how do they connect to each other. All right, so information theory is really the theory of what information is, and we will first give a meaning to information, a mathematical meaning. And then we're going to connect that to statistical estimation, to statistical inference, okay? The information theory was born in 1948 and was developed by Claude Shannon, who was an engineer in MIT at the time. And really this paper laid down all the foundations of modern information theory, which are at the core of signal processing, communications. All the numerical world is essentially a consequence of these notions we're going to discuss. All right, so let's be very concrete and define right away the most important quantity in information theory, the most basic one, which is the so-called Shannon entropy, okay? So this is a quantity introduced by Shannon in this paper, but the name entropy was already there for a long time. So for those of you who know a bit about physics, and in particular statistical physics, the notion of entropy is already there for at least a century in statistical physics, okay? And the reason why Shannon called his definition of, we will see, information content entropy is not by luck. It's precisely because this quantity is fundamentally linked to the notion of entropy in statistical physics. I will not develop in this lecture this notion, but we will see in the next lectures that indeed what we call entropy, free energies, quantities like this in statistical mechanics are really linked to the same notions in information theory. These are basically two sides of a same coin, okay? All right, so let's start by just defining the entropy. So the entropy of a random variable, so I will consider at the moment only discrete valued random variables. So here is x, a discrete valued random variable with probability p. And I will call, so I will be slightly loose in the notations. I will both call the random variable itself capital X, and I will also call its possible outcomes with the same notation. But given the context, it should be clear whether I'm talking about the actual random variable or one of its outcome, okay? For example, it's inside a sum or an average. I'm talking, so for example, here, if I'm summing here, of course, these are the possible outcomes, the possible values that this random variable may take. If you see a quantity like this, expectation with respect to x of some function of x, here the x in the argument should be thought as the random variable because I'm averaging over it here, okay? Perfect. So the Shannon entropy associated with a random variable, or equivalently associated with its law, because this is only a function of the law of the random variable, is the following. It's a sum over all possible outcomes of the variable of their probability times log of 1 over the probability. Okay? So this can be interpreted as an average. You see that this operation there is an expectation. It's the expectation with respect to x. It's the expectation with respect to x of without the log here. This is the expectation with respect to x. And it's the expectation of what we call the information content or surprise. So let me define this little h of x as the log of 1 over p of x. So here, in this case, the x should be thought as a possible outcome. Okay? So, for example, if you have a coin, the outcome could be a head. Okay, while the random variable is the coin that can have head or tail as outcomes. Okay, so the surprise associated with an outcome is the log of 1 over its probability. So why is that somehow natural as a notion of surprise? Because you see that if an event, an outcome, has a low probability, so p of x is close to 0, then log of 1 over something that is close to 0 is large. So if an event has a low probability to occur, then its associated surprise is high, in the sense that if you would observe this event, this outcome, you would be highly surprised because it's simply an unlikely event. Okay. On the contrary, if p of x is close to 1, so if an event is highly likely, then its surprise is low because you get log of 1, you get something close to log of 1, which is essentially 0. Okay? So highly likely event have a low surprise. Of course, you could define many functions with this property in the sense that it would be high when p of x is close to 0 and 0 when it's close to 1. There are infinitely many choices of functions that would verify this property, so this is not enough, of course. But this is already an indicator that this is a valid candidate of what we could call the surprise. Okay. And you see the entropy is therefore the average surprise, right? I can rewrite this as the expectation with respect to x of little h of x. The entropy is the average surprise. Okay, so you can define, by the way, the entropy with different normalizations for the log. So this is the log in natural units. In this case, the entropy is defined in terms of what we call nats, which stands for natural units. If you take a log 2, the entropy would be written in bits. Okay, perfect. So let's now give some more meaning to the entropy. So I would like to essentially convince you of the following facts. Okay. The first fact I want to convince you is that the Shannon entropy defined before can be thought as its average information content, namely the expected information gain when observing the outcome of a random variable. So conceptually, you can think of a random variable, as long as it's random, it hasn't taken any value, so you haven't observed the outcome of this random variable, so it is an uncertain object. Okay. Basically, the entropy can be thought as how much information would you gain if you observe the outcome of this random variable, and this in average over all possible outcomes. Okay. So imagine the following experiment. You are in the desert. You're walking. Okay. And you observe that it's raining frogs. Okay, suddenly it rains frogs. This is slightly weird, right? So it is a highly unlikely event. The fact that it rains is already unlikely in a desert, but the fact that it rains frogs is even more unlikely. And this is so unlikely that actually it should make you realize that you're probably dreaming. Okay, so you see, this event is very unlikely, and therefore it has a high informational value. The fact of observing such an unlikely event brings you a lot of information. Okay. Now suppose the opposite. You are in the desert and it's very sunny and hot. This is a very likely event given that you are in the desert. So even if you were dreaming, you would not realize it, right? Because the fact of observing hot weather in the desert is extremely likely and therefore has a low informational value. The fact of observing this outcome of the random variable weather, the weather in the desert, would not bring you any information, and yet additional information that you already have, the fact that you are in the desert. Okay, so if you are averaging all these information gains associated with all the different outcomes, you get the average information gain, and this is the entropy. Okay? But you can also think the entropy the other way around. You can think of the entropy as the average uninformation or lack of knowledge about some random variable. So it sounds weird because it seems that I'm telling you right now the opposite. I just said that the entropy can be thought as potential information gain. How much information do you gain in average when you observe the realization, the outcome of a random variable? Now I'm telling you that you can also think of this as the average lack of information, the amount of how much do you not know about a random variable. But this is exactly the same. It's just a conceptual shift, because the information that you gain is what you gain when you do observe the random variable outcome, right? But prior to observing the random variable, you actually do not know a lot about this random variable. And the more this random variable is unpredictable, in the sense that the more some events are unlikely to happen compared to others, the more you know, the more you would gain when observing it in average, because potentially you will observe unlikely events with a high informational value. But at the same time, it means that before observing the realization of the random variable, you know less, right? So essentially, the fact of observing the outcome of a random variable converts a certain amount of uninformation, of lack of information, into information, okay? So it's just conceptually placing yourself before or after having observed the outcome of the random variable, okay? So you can equivalently think about the Shannon entropy as the potential, the average information gain that you would get when observing the outcome, or equivalently as the average uncertainty, the average lack of information about the random variable. Okay? These are just the same thing, right? The entropy is quantifying, so from what I just said, the amount of unpredictability of a random variable. So essentially, the higher the entropy, the less you know about this random variable, about its outcomes before observing it, and therefore the more unpredictable it is. Okay? So what is a variable with the smallest entropy? So which is the less unpredictable, or the more predictable, if you wish. It's simply a deterministic variable. It's a variable that always takes the same value. It's not random. In this case, the entropy would be 0 because without having to observe it, you know in advance what value it takes because it does not fluctuate. Okay, it cannot take any other value. The extreme opposite is the uniform distribution. If all outcomes of a certain random variable have the same probability, in average, it is the most the one that brings the highest surprise in average. Okay, so it is the most unpredictable essentially because any outcome can happen with the same weight, so you cannot say much about it before observing it, right? Okay, so this was for interpretations of the entropy. Let's now see formal properties, mathematical properties of it that suggest that what I'm saying makes sense. Okay, that this is the right notion of information content carried by a random variable. Okay, yes, here I want to mention one thing. The entropy h of x is the expected number of yes-no questions that you would answer when observing the outcome of a random variable. Basically, or the other way around, if you do not know the outcome and you want to know, let's say someone observed the outcome of a certain random variable, the weather in some place in India at a given day in some region. So this was observed by someone that therefore know the outcome of this random variable. From your perspective, this is still a random variable. You don't know this weather yet. And you're trying to guess what was the weather on that day. So you start asking to that person questions of the yes-no form. So was it raining? No. Was it hot? No. And you can ask a number of questions until you get to the answer. Okay. And basically, the entropy of a random variable quantifies how many such binary questions you would need to ask to identify with certainty the outcome of this random variable. Okay? Okay. Perfect. So this I already said. The entropy is never negative, by the way, from the definition, you can check. And it is equal to 0 only if the random variable is not random. It is a deterministic variable, meaning that there is a single outcome indexed by I here that would take all the probability mass. So Pi would be equal to 1 for a certain I. Okay. In this case, the entropy is 0. There is no uncertainty about it, or equivalently, observing it would lead no information, that additional information that you don't already have. Okay. And like I said, the entropy is maximized for the uniform distribution. Okay. Only when all outcomes have the same probability, which is 1 divided by the number of outcomes, which is this symbol here, then the entropy is maximized. Okay, so there are some nice properties that we can show for the entropy. In particular, the fact that it is the average of the surprise here, minus log x, implies something nice. If you take two random variables which are statistically independent, so this notation means that the joint law of x and y is just the product of their laws, then the surprise is additive. Of course, you have minus log of p of xy equal minus log of p of x times p of y for independent variables, which is minus log of p of x minus log of p of y. So the surprise is additive for independent random variables, and therefore the entropy as well, because it's just the average. The average is a linear operator, so the average surprise is as well additive if the surprise itself is additive. Okay. So what does it mean? It means that if X and Y are independent, the total information carried by observing both is the sum of the information carried by X only plus the one carried by Y. Of course, they are independent. Okay. This entropy there is defined as before. So this is called the joint entropy. So it is the very same definition, except that now we're talking about more than one random variable, in this case a pair, but actually the definition has to be the same because you can always think of a pair or any vector of random variables as just a single one random variable, but it's just a vector. So the definition is the same. I'm summing over all possible outcomes of this pair of random variables of the probability log of 1 over the probability. Okay, so this is the average surprise carried by the couple of random variables. So it's called this is also called the shadow entropy, but for the pair. Okay, let me define another notion of entropy, which is important, which is called the conditional entropy of X given Y. So the conditional entropy is defined similarly, except that now, you see, I'm averaging with respect to the conditional law of X given Y log of 1 over P X given Y, and I'm averaging over Y as well. I can also write this as the joint law. Okay? So the meaning of the conditional entropy is the information like the expected information gain when observing the outcome of random variable X, given that you already know the outcome of Y. So how much information can you still gain when observing X if you already know Y? Or the other way around, again, there is the unpredictability interpretation. This is the remaining uncertainty about X, given that you already know about Y. Okay? Very simple. Okay, so a very nice property of the entropy is the chain rule. So the chain rule is telling us that the total information carried by the pair of random variables X, Y can be decomposed as the information carried by Y alone plus the remaining information carried by X when you already know Y. So you see, this tells you what Y brings, and this tells you what X brings that remains, right? So this equality is very natural. But of course, I recommend you to try to prove it. It's very simple, and it just follows from the definition that I gave before. It's a one-line proof. But you can also write it the other way around. So the total information is the one carried by X plus the remaining one carried by Y, given that you already know X. Okay. Another important property is that this is a form of what we call a data processing inequality. So if you apply a certain function to a random variable, any function, okay, you can only decrease the entropy, or at best do not decrease it. It can remain equal, but you cannot increase the entropy by applying a function to a random variable. So basically it means that whatever random variable, you can process it in any way, you can apply any function you want. The total amount of information carried cannot be changed. It's a kind of conservation of information. Okay, you can only lose information. You cannot create information out of nothing. Okay, it's a bit like energy in physics, if you think about it. And actually, there are many parallels between energy and entropy. Okay. Okay. And the equality here stands. So this is an equality if and only if f is invertible. okay? If you can uniquely invert this function, then considering the original variable or the processed one, it gives the same amount of information when observing its outcome, because you can go from one to the other in a one-to-one way. Okay, another property, if two random variables are independent, again, then the conditional entropy is just the entropy. Again, once you have absorbed these notions, what entropy means, you don't even need to prove this. It's kind of direct, right? The total unpredictability about x given y is just the one of x if x and y are independent. It has to be the case, and indeed it is. You can prove it. Okay. Finally, let me emphasize this last property. The total information carried by a pair of random variables is less or equal than the sum of the information carried by both. Okay? So again, this is an equality if and only if x and y are independent. And the fact that we have an inequality in this direction is natural, right? Because again, if x and y depend on each other's, okay, if you observe one of them, it already tells you something about the other. So it reduces the potential information gain carried by the other. So the inequality has to go in that direction, okay? Okay, so before moving to the next definition, is there questions on the entropy? Okay, so I guess these are notions that you're familiar with. Perfect. So let me now move to slightly different thing. Let me just mention quickly here, even if this is not so important for the rest of the discussion, but
Excuse me, sir.
yes.
Can you please explain the last statement? What you explained?
Here?
Yeah, this one.
Yes. So I'm saying that you see, you have an inequality that tells you. Let's think in terms of uncertainty. Maybe this is conceptually simpler. What is the total uncertainty about a pair of random variables? It has to be less than the uncertainty of one plus the one of the other. Because you see, if the variables depend on each other's, when you measure one, when you observe one, it tells you something about the other. So it reduces the uncertainty about the second one. So that's why the inequality goes in that direction. Instead, if the two random variables are independent, this is an equality, okay? So I don't know if this is clear, but when random variables are dependent on each other, observing one tells you about the other, and therefore you can only get a reduced uncertainty. So maybe I can prove it. This, you can see it like this. Let me prove it. So take the chain rule. Okay, we have the chain rule there. And what I'm saying is that, so I write the chain rule, which is h of x, y equal h of x given y plus h of y. And what I'm saying is that this is necessarily less or equal than h of x. The uncertainty about x given y is always lower than the uncertainty about x. Basically, observing something cannot reduce the amount of information. So you see, the fact of observing something has to reduce the uncertainty. This is information. An observation is information. So you have to reduce the uncertainty. Is this inequality clear?
Yes, sir.
Okay, so I'm using this inequality from the chain rule to show this one. Okay? Perfect.
Okay, sir. Got it. Thank you.
Perfect. Thank you for the question. Let me just mention that everything I said is kind of, let's say, exploiting the fact that we're working with discrete random variables, but you can generalize the notion of entropy, of shell entropy, to real valued random variable. And this notion is called the differential entropy. Okay? So the differential entropy is defined similarly. You see that we have a kind of surprise here. This is the log, this is minus log of the density of the random variable. And I'm averaging over it with this integral against fx. Okay? So, so this is the natural generalization, but one has to be a bit careful, because with continuous variable, for example, this differential entropy is not necessarily non-negative. So the Shannon entropy of a discrete random variable cannot be negative, and so this is a natural property one wish for a notion of information. There is no such thing as negative information. You cannot lose information by observing something. However, the differential entropy can be less or equal than 0. Okay, so it's a bit less natural to think of it as an information content. However, for continuous variables, there is a slightly different object which will recover the correct, let's say, properties that make it a good candidate of information content. Instead of working with entropies, with continuous variables, we will work with differences of entropies. Okay, and this will be the mutual information, and this is the correct notion to work with when you have continuous variables. We'll do that now. Okay, so in order to define the mutual information, I first need to define another thing, which is the Kullback-Leibler divergence. Okay, the Kullback-Leibler divergence is defined like this for discrete or continuous variables. So this is again an average over some probability distribution P of x of the log of the ratio between two probability distributions. Okay, so this is for the discrete case, and you have the continuous case below. So notice that this this definition is non-symmetric, which is emphasized by this symbol here, this double bar. The fact that P is on the left and Q is on the right here means something. Okay, if you were putting a Q there and a P there, you would have a Q there and a Q there and a P there. So this is a non-symmetric definition. Okay, so the meaning of this object is a kind of measure of inefficiency of assuming a certain distribution when the true distribution is P. So what does it mean this concretely? It means that if you are trying, so let's say you are sampling the distribution P. You obtain outcomes from the random variable whose distribution is P. So you, let's say there are sequences of numbers or of words, okay? And you're trying to compress, using some compression algorithm, these sequences, but as using a compression code. So it's an algorithm that tries to find a more compressed representation of these sequences without losing information. So you're just trying to find the proper representation such that with less symbols, you can kind of keep the same amount of information carried by these sequences. But you're using a compression code that was not optimized for samples from the distribution P, but instead for samples drawn from the distribution Q, which is different. So your code is not optimal for P, it is optimal for Q. So you are not using the right compression code, if you wish. And this DKL is kind of telling you how many bits you are going to use by using this compression scheme that you could have kind of not use if using the proper compression optimized for P instead. Okay? Okay. So it's a measure of essentially how distances, like how probability distributions are far from each other, that you can think in terms of compression. Okay. By the way, as I mentioned in the lecture notes at the beginning, if the kind of things I'm saying here are really new to you, I'm sure that everything I'm saying is therefore not so trivial. And there is an amazing book that I recommend, which is by David McKay, that you can find on internet, which is free on his website. There is a link on the notes I give. And you have tons of examples, very detailed. It's extremely clear. This is really one of my favorite science book for information theory, inference, machine learning, for tons of things. So I highly recommend it. Okay. So for example, if you compute the KL divergence between two Gaussians, let's say they have the same variance, but they have a different mean, mu1 and mu2, what you obtain is the following formula. So you see that it diverges as a square of the difference between the means. Okay? Okay, so this KL divergence has a number of properties. So in particular, this is not a true distance, because the distance is always symmetric. The distance between point A and B, so here the points we're talking about are probability distributions that live in the space of probability distributions. If you take probability distribution 1 and 2, 2 points, a correct notion of distance between the two is that the distance between the first and the second is the same as between the second and the first. This is not a symmetric object, so this is not a distance in the geometrical sense. This is something else, but this is a notion very useful. It has a number of properties that I won't discuss. You can take a look, but in particular, it's never negative. Okay, it's only zero if P equal Q. So it's not a distance yet. It is zero only when these distributions match. So it shares features with distances. Okay. Okay. Now let's move towards notion which will be really central to this course, which is that of mutual information, which is the following. So we will see that through this notion, why is it central? We will see that if we are able to compute this mutual information that I'm going to define now, we will have directly access to the performance that one can aim for in the best possible case, the performance of Bayes optimal estimators that we define through Bayesian decision theory. And this is really the ultimate goal of this course in the context of high-dimensional inference. Okay? So this is really a key object. So let me define it. Take a pair of random variable xy. Okay? The mutual information, which is a symmetric notion now, okay, contrary to the Kullback-Leibler divergence, the mutual information between x and y is the same as between y and x, and this is the reason why people use a dot comma here. It's to emphasize the symmetric nature of this object with respect to its arguments, is by definition the Kullback-Leibler divergence between the joint law of the two random variables and the product of their individual marginals. So just that we're on the same page to make sure that some notion is not missing to you, what is the marginal of a probability distribution? So if you have a pair of random variables, you can obtain the marginal of x, let's say, by integrating with respect to y their joint law. Okay, so this is the marginal. And of course, you can obtain the one for y by integrating with respect to x. And this operation is called marginalization. Okay? So you are looking at how different, in the Kuhl-Black-Leibler sense, is the joint law of the pair, when you really consider them together, how different is this distribution from the product of their individual distributions, as if you were considering them independent. Okay? So it is from the earlier definition, we get this definition here. So this is the average with respect to the joint law of the pair of the log of the ratio between the probability of the pair divided by the product of the probabilities of the individual events. Okay? You can also define the same thing for continuous variables by replacing this sum by integration, and these probabilities become densities. Okay? But the definition is the same. So, okay, this is a bit an abstract definition. Let me try to convince you now again with words. Why is this a correct? Why is this a nice object to look at? Why is it so important? So again, you can really think of it as a kind of distance between 2 points, where these 2 points represent the joint law of the pair and the product measure. This is the product of the marginals. And the more these 2 points are distant from each other somehow, the more these 2 random variables should depend on each other's, right? Because here it means you are forgetting the dependence between the 2. Here you are considering it. And if this distance is big, it means that they are strongly dependent on each other's, because it means you cannot approximate the joint law well using the product of the marginals. Okay? If 2 random variables are weakly dependent on each other's, it should be a good approximation to consider their joint law as just the product of their individual laws. In this case, this Kuhl-Black-Leibler divergence would be small. But if they are strongly dependent on each other's, it should be high. So it measures the amount of dependence between random variables. Let's now use our understanding of what Shannon entropy is and place ourselves in the context of signal processing, signal extraction, of inference, in order to make more sense about this quantity. Okay?
So I want to ask a question. So
Yes.
Earlier, when we were doing KL divergence between P and Q, we were talking about like if how much more bits we needed to encode samples from P using the encoding scheme optimized for Q. So
Yes.
in this case, in the information sense, what does it mean that we are in the information definition where we are doing KL divergence between the joint and the marginals?
Yes.
How to think of it in terms of codes?
Yes.
Is there a way? Yes,
Yes.
I just wanted to ask.
Thank you for the question. So let me try to, all of you, please stop me when you have questions. I mean, that's really the point of these lectures. So thank you for the question. So if you want to think in terms of codes, you see, this kind of quantifies the additional number of bits you will need to code if you were, so imagine the following experiment. You are generating sequences of pairs of random variables like this. So you have realizations of xy. So you have the first realization, you have xy11, x2, y2, okay, xn, yn. These are realizations of the pair of random variables, okay? And you are trying to compress these sequences. Think of this as the first word, okay? This is the first word in a two-word sentence. This is the second word, the first word, second word, and you are trying to to code these sequences efficiently. So to find a compressed representation that allows to keep the information carried by these sentences, but with the smaller number of bits. Okay. If you are assuming that the word 1 and 2 are completely independent, have been picked randomly in the dictionary, one after the other independently, then you have a certain compression code associated with this assumption. And if you try to compress these sequences with this code, it would give sequences of a certain length in bits. But if you do so, it means you are using a code optimized for this distribution. This is not a very smart choice because, of course, there is a structure in a sentence. The second word is not picked randomly after the first. For example, if I tell you I, there is a higher probability to pick the word am or I do rather than car or dog, right? So if you're kind of forgetting these dependencies between words and use a code optimized for the cases where the words are picked independently of each other, this would be a bad code. The compression would be not good. And the information, the number of bits you would require in addition that you should not need if you were exploiting the correct dependencies between words is quantified by this. Does it answer your question?
Understood, sir. Yes, sir. And the reason, like, we could have the P and Q places swap in the mutual information. Is there a specific reason why the joint is on the P side and the marginal products are on this Q side of the GIAN divergence?
Exactly.
Is there a specific reason?
You mean why we don't put it the other way around?
Yes, sir.
Because if you do so, you will lose the identities that I'm going to write next. This is not the correct definition. There is no short answer. It's just that what I'm going to say next does not apply, and therefore this is not the correct one. Okay?
Yes, sir.
Okay, thank you for the question. So let me continue. So if now we have two main definitions. We have the Shannon entropy at the beginning. We have the Kuhl-Black-Leibler divergence. You take these two definitions together and the mutual information, three definitions. What you realize directly is that the mutual information can be written in terms of Shannon entropies. In particular, the mutual information between X and Y is the entropy of X minus the conditional entropy of X given Y. So let's think again as X as the unknowns, or what you call in signal processing the signal, and Y is the data, and it's a function of X, is the observed data. Okay. This interpretation, this identity is then very natural. Okay, what does it tell you? It tells you that the mutual dependence between X and Y, so essentially the amount of information carried by the data about the signal, or vice versa, because this is a symmetric notion, but I think it's more natural to think as the data carrying information about the signal, is what? It is the uncertainty about X. Okay, so how much you would potentially gain if observing X, which is equivalently the amount of an unpredictability about X. So this is the uncertainty about X minus the uncertainty about X that remains when you observe the data. So it's essentially a reduction in uncertainty. Okay, so if Y, the data, is independent of X, this is simply equal to that. So observing the data would not reduce the uncertainty about X, and therefore the mutual information would be 0. Okay, so the reduction in uncertainty about the signal when observing the data would be 0 because they would be independent. Okay, so this is the first notion, the first interpretation. It's uncertainty reduction due to data observation. But you can write it the other way around. You have also this equality, you can do it. What does this say? It tells us, now instead of thinking of uncertainty, I want to use the dual meaning of entropy, which is information gain, okay, the information content. The mutual information between my signal and data is the total information carried by the data, okay, minus the remaining information carried by it when I already know the signal, okay? But what does it mean, this object? If I already know the signal, what is the information carried by the data? What does it even mean? It's simply the contribution due to noise. We're always thinking of a noisy process. You have a signal which is corrupted by noise, and then the data is this noisy version of the signal. And so there is part of what Shannon calls the information, which is also related to the noise. You cannot forget it. We call it as noise in a given specific problem because this is the component that we do not care about. But information theory is agnostic about what you, for a given problem, care about or not. It's still something which is in the data. Okay, so the notion of noise is a subjective notion. What is signal, what is noise depends very much on what the task that you're studying, okay? Maybe for someone else, given the same data, they want to reconstruct what you call the noise, and the signal for you is what they do not care about. So it's subjective, okay? So thinking about X as the signal and the remaining in the data as the noise component, this term is precisely quantifying the information carried by the noise component. That is what remains when you already observed what you call the signal X. Okay? So this is the total information carried by the data minus the information about the noise. And so if you remove the information carried by the noise, it means that this is indeed the information carried by the data about the signal only, because you remove the noise component. Does it make sense? So this is the noise component or contribution to total information in Y. And so if you, this is the total information. So if you remove the noise component from the total information, what remains is what the data tells you about the signal only. Okay? So it's a very natural object to look at. Okay, perfect. So Jaspal, can I do 10 minutes more, or is it too late? Okay, we'll assume the answer is yes. So let me continue. Because I think that the lectures are basically between 1 and 1 hour 30. So let me take a tiny bit more of your time. So let's define, let's see additional properties of the mutual information. First, let me just define the conditional mutual information. That is, what is the mutual information between X and Y conditional on a third random variable? And this is just the same as before. It's the KL divergence between the joint law of X and Y given Z and the product of their marginals given Z. Okay? So this is the very same definition as before. It's very natural. And again, you can write down this as difference of entropies or differential entropies if you're working with continuous variables. But the interpretation is the same. It's just that now everything I just said applies, but given the observation of another third random variable that was already observed. Okay? But it's the same. So some important properties: the mutual information is symmetric by definition. It is non-negative, and now this is always non-negative, including for continuous random variables. So this is what I meant by this is the correct notion to keep in mind for information content, including for continuous variables, because this is always non-negative. So now you are kind of looking at Shannon differences, and the fact of working with differences makes the entropy the correct notion of information carried by one variable about another one. Okay, you are comparing. An important property is the data processing inequality. So it tells you that if you have a Markov chain, so Markov chain means that so this symbol means that the probability distribution of x, y, and z can be written as the probability of x times the probability of y given x times the probability of z given y. In general, here I could put an x as well, but if you already know y for z, you don't need to know x anymore. It becomes independent of x. So this is what a Markov chain is. And the data processing inequality tells you that the mutual information between x and y has to be at least the one between x and z, which is very natural because in the middle there is an operation that happens there. And you cannot increase the information. Okay, this is what we mean by data processing inequality. You can only decrease information. Okay, so in the best case, this y is a invertible function of x. It's a one-to-one function of x. In this case, the mutual information between x and y and x and z would be the same. But if it's not invertible, you would lose something. Okay, if this step has some noise, if you want, you would lose some information. Like for Shannon entropy, we have the chain rule. Again, by definitions, you can try to prove these properties. It's very simple. So the total information carried by the pair yz about x, or vice versa. Notice that here there is a dot comma here, while here it's a normal comma. So it means that we're computing the mutual information between x and the couple xy, which is like one random variable. This is the total information, this is the mutual information between x and y, plus the remaining information carried by x about z when you already know y. Again, it's the same type of decompositions like for the entropy. It's very natural. Okay. Okay. Maybe we should stop there, and at the beginning of the next lecture, I will show you this very important result, which is really what motivates this lecture of introducing mutual information and all that. The reason we will see is that if one knows the mutual information, you can take a certain derivative of it with respect to the so-called signal-to-noise ratio. I will introduce that better at the next lecture. You directly access the minimum mean square error. Okay, this is the error between the signal and the base optimal estimator, which is the posterior mean. You remember first lecture, Bayesian decision theory. The posterior expectation is the best estimator in the universe if you are considering the Euclidean distance as a loss, which is what I'm considering here. So this is really the goal. We want to compute this quantity, which will lay down fundamental bounds to the performance of any inference procedure. But to compute it, we will first need to access the mutual information. And then by derivation, we will get it. Okay? Perfect. So we'll repeat that next lecture, and so we see each others in I guess in 45 minutes. Or Jaspal, are you here? Okay, so let's disconnect and let's reconvene at the normal time, which is which for you is 4:30. Okay, which is in what time is it for you? Which is in 50 minutes. Okay. Is there any question or? Okay, no question. So I assume that it was clear. So see you in less than an hour.
Good evening, everyone. Am I audible?
Yes, ma'am.
Okay. John sir, should we start? ये लोग कैमरा नहीं हो सकते अब रिकॉर्डिंग नहीं ना करनी I welcome you, sir, back again. So we may start. I request all participants to join.
Okay, I was muted. Just to be sure, the previous lecture people were hearing me, I guess, I hope.
Yes, sir. Now we can hear you.
Yeah, at the previous lecture as well, I hope so that I was not talking alone for an hour.
No, sir. Yes, last 5-10 minutes I got out of internet, but you were there. I could hear you throughout.
Okay, perfect. So I was just quickly summarizing what we've done last lecture. We've laid down the foundations of information theory. We introduced the notion of Shannon entropy. We have shown through its definition and some of its properties that it's a good candidate for a notion of information content carried by a random variable. We've seen that it equivalently quantifies the average information content or the amount of uncertainty about this random variable prior to observing its outcome. We've seen then what's the Kullback-Leibler divergence, which is a notion of discrepancy between probability distributions. And we've seen that when using the Kullback-Leibler divergence to the joint distribution of random variables and compared with the product of their marginals, this defines the so-called mutual information. And we've seen that the mutual information is indeed a good notion of information content carried by one random variable about the other. And conceptually, we think of one of the random variable as the data, which depends on some unknown parameters, on some unknown signal to infer, and the mutual information as a natural meaning of how much the data depends on the signal, and therefore how much information it carries about it, and not about the noise, which is the complement of the signal in the data. Okay, so now I would like to bridge the first lecture on Bayesian inference and the second on information theory by showing to you that the mutual information is actually directly connected to the minimum mean square error, which is, as you recall, the error in the L2 sense, in the sense of Euclidean distance between the ground truth signal to infer, the unknown parameters to recover, and our estimator. And the best estimator that minimize in the average sense, in the Bayesian sense, that minimize the risk associated with the L2 loss is the minimum mean square estimator, the Bayes estimator, which is nothing else than the expectation, the mean of the posterior distribution. So I want to compute the error associated with this posterior expectation, and this I can do it if I know first how much information does the data contains about the unknown parameters, the signal. I will call it the signal from now. And this relation is the so-called IMMSE formula. Okay, so this is the fundamental connection between information and estimation. Okay, so the generic formula goes like this. So imagine that you have data y. So this y can be anything. It can be a scalar random variable. I mean, it can be a scalar variable. It can be a vector of observations, a matrix, a tensor. It doesn't matter. Will be observed. Will be obtained as data plus Gaussian noise. Okay, so my data again is x, and the noise is z here. Okay, so the dimensions match, and this z is made of independent Gaussian entries with zero mean and variance 1. Okay, so the formula, the IMMSE formula, tells us that if I'm able to compute the mutual information between my signal and my data, corrupted by Gaussian noise, then by simply taking the derivative of this mutual information with respect to the signal to noise ratio, this parameter lambda, which belongs to R plus, is called the signal to noise ratio, or SNR, which quantifies essentially the strength of the signal component in the data with respect to the noise. So if I take a derivative of the mutual information with respect to this SNR, I get directly access to the MMSE, the minimum mean square error, times 1/2, where again, the MMSE is the expectation And here, this is an expectation over everything. So this expectation is an expectation over the parameters to infer and the data. You can decompose it, which you can decompose like this. It's signal and then conditional distribution of the data given the signal. Okay, which is equivalent to expectation over signal and expectation over noise. Okay, because this random variable y conditional on x is nothing else than the noise. Okay. So if I take an expectation there over everything of the L2 loss, the Euclidean distance between the signal x and the base optimal estimator of it, this is x base. This is given by this derivative. Okay, so we have a formula that directly connects a notion of information content, which is the information that the data carries about the signal, and estimation, which is the best error one can aim for when estimating x using the best estimator possible, which is the posterior mean. Okay, so this is really a fundamental relation that links estimation and information. If time allows, I will prove it. I'm not sure, but the derivation is surprisingly simple. So it's written in the lecture notes. I will show you where, but you can try by yourself. It's a simple exercise. I mean, once you see where to be careful in the computation, it's really simple. So it's an exercise. So let's discuss what this means. So okay, this we said. So what is important to know is that the mutual information as a function of the SNR, okay, in this model there, and the model we're going to study will be a model of this form, meaning that the noise will be additive and Gaussian, which is a very standard notion of noise. The mutual information seen as a function of lambda is an increasing function. And so the minimum mean square error, the best error we can achieve, is related to the derivative at a given point here of the MMSE. And therefore, the derivative is increasing, and of course, the MMSE is a positive constant. It's a positive object. So this derivative is increasing, but this derivative is slowly decreasing as the SNR increase. So it's a concave function, and so therefore, as the SNR increase in this direction, the MMSE decreases as it should. The higher is the quality of the data, controlled by this signal-to-noise ratio. The more there is signal in the data compared to the noise, the lower should be the achievable error, right? And this formula says so, because this is a concave function, and so the derivative decreases as lambda increases. Okay, perfect. Any question on this formula before I move on to the next? Or is the meaning clear? Okay.
Sir, here,
Yes.
in this, we are saying that as the gradient of this information function as a function of SNR it increases, the MMSE decrease. Could you please repeat it again?
Yes.
I was.
So this relation here is not telling us that so this is the MMSE, right?
Yes,
this is the best error we can achieve. What the formula tells is that the MMSE is related to the slope of the mutual information as a function of the SNR. So what we'll be able to show is that the mutual information is actually a function that looks like this, like what I represented there. It's a function that increases with lambda, okay? Because the more the data depends on X, the more the mutual information should increase by definition of what the mutual information is. So it's an increasing function. But at the same time, the slope decreases as lambda increase. So because the slope here is the minimum mean square error, it means that the minimum mean square error will go down as the SNR approaches infinity. In the limit where lambda goes to infinity, this curve becomes very flat, and here the slope tends to 0. I prime as a function of lambda tends to 0. And indeed, the best reconstruction error you can achieve when the signal to noise ratio tends to infinity should be 0. It means that you have no noise, and so you can perfectly reconstruct the signal. Okay?
Understood, sir. Thank you, sir.
You're welcome. Thank you for the question. All right, so let's now move to the definition of the main model we're going to study from now on. Okay, so again, I want to repeat that we're going to study a specific model, but many things that I'm going to say apply much more broadly. Okay, so there is not much of a loss of generality to focus on this model that is called the Spike-Wigner model, because it extends. Okay, so the first thing I want to mention is that this course is about a peculiar setting of Bayesian inference, which is called the Bayesian optimal setting. So what does it mean, Bayesian optimal setting? It means that as a statistician that tries to perform inference, you are using the correct prior distribution and the correct likelihood. It means that somehow it's an idealized model, an idealized setting, where the ground truth unknown parameters you're trying to infer are generated according to some probability distribution. Then there is a data generating process. You go from signal to data, which can be modeled according to a conditional distribution, P of y ln x. And these distributions are both known to the statistician. So the statistician is correctly exploiting the prior information about the signal and is modeling the way the data generating model in the correct way. So there is the statistician is a kind of perfect statistician. They know perfectly how the signal and the data were generated. What they don't know is what is the precise realization of this signal. Okay, they think of this signal as a random variable with a certain probability distribution that they know, but they don't know what outcome of this random variable is out there. They want to recover this outcome. Okay, but these two distributions there are perfectly known by the statistician. Okay, what does it mean? Is that it means that the statistician can write down the Bayesian posterior distribution correctly. They can use the true posterior distribution of the signal given the data. Okay, and so this is what we mean by Bayesian optimal setting, because you see what I'm describing is a setting which is the best you can imagine. This is a setting where the only thing you don't know is the precise value of the signal, the unknown parameters, but you know how it was generated according to which probability distribution. So you know correctly all prior information there is to know about it. And you also perfectly model the way the data has been generated conditional on it. Okay? So this is optimal in this sense. And this is the setting that one should study in order to study the fundamental limits of inference. Because this is a setting where all prior and information, all the information is exploited correctly. we study the performance of estimators that are based on the correct posterior distribution. There is no mismatch, no errors, okay, no modeling error. And therefore, a statistician that places themselves in this setting should be able to reach the best possible reconstruction error. Okay? So we're going to focus on this. If you start to have mismatch, for example, a statistician that would assume instead of the true prior distribution Px, they would write down a posterior distribution based on, let's say, another probability distribution P tilde of x, which would not be the same. This is called a mismatch. And this leads, of course, to a decrease in performance of inference, of course, because you are making wrong modeling assumptions. But we're not going to consider that, okay? Perfect. So a very simple and at the same time profound implications of working in the Bayesian optimal setting is called the Nishimori identity. So Nishimori identities is a term that comes from physics, but in statistics, people simply call that the Tower property of conditional expectation. It's a thing you already know. It's very simple. This is this property there that you can write down. We already used it. You can write down a joint expectation with respect to data and signal, so y and x, as the expectation with respect to the signal times the expectation with respect to the data given the signal, or the other way around, the expectation with respect to data times the expectation with respect to x given y. So you see here, in this expression there, I should not think of the x random variable that I'm averaging over by this operator here as the signal, because it's kind of drawn conditional on y. So it should be thought as a posterior sample. This expectation is with respect to the posterior. So you see, it means that the full expectation can be decomposed as prior expectation times likelihood expectation, or as expectation with respect to data times posterior expectation. Okay, so this is called just the Tower property. And using this, you can get many simplifications. And in particular, so here there is a generic theorem that you can take a look. But this theorem is basically telling you that if you take any function, forget this x2, xk, let's simplify just a bit for the purpose of, then you can read the more generic statement if you are interested. Let's say we have a function that depends on the data and on x, okay, where x is really the unknown parameters. It's the ground truth signal we're trying to recover. If I take an expectation of this function of y and x, both with respect to the posterior, this is what this bracket means, this bracket here, and I will use repeatedly this notation, so put it in your mind. The bracket will be a special symbol to denote an expectation with respect to the Bayesian posterior distribution, okay? I will not use this bracket for any other type of expectations, only with respect to the posterior. Okay, so if I take, so I can write it like this, it's the same. Okay, if I take an expectation with respect to the data, this is an expectation with respect to the data, and with respect to the posterior of a function that depends on data and the ground truth x, then I can replace in it the ground truth by a sample from the posterior. This is what this x1 means. This x1 is a sample from the posterior distribution, not anymore from the prior. Instead, the x is drawn from the prior. Okay? So you see this Nishimori identity, which is a direct consequence of the Tower property here. The proof is one line. You can read it there. You can do that later. Is telling you that inside expectations, you can replace the true signal by a sample from the posterior distribution. Statistically, in average, they're the same. And this comes from the fact that we're considering this Bayesian optimal setting. The statistician is making no modeling error. Okay, and doing so, there is a statistical equivalence somehow between signal and samples from the posterior distribution. Okay, so one direct consequence of this, for example, is that the minimum mean square error, which is really we defined like this at the moment. Okay, so this is the average Euclidean distance between the ground truth X star and the Bayesian optimal estimator, which is the posterior mean, which I now denote with a bracket, as I said. Okay, this minimum mean square error can be written equivalently like this, which is actually the variance of the posterior distribution. The way you can see it through this Nishimura identity is the following. This, which again is this, is just a function of the data. Okay, this bracket is a function of the data only. I'm integrating over X, so it only depends on Y. So what I have is inside here I have a sample from the posterior distribution. This is this capital X that before I denoted X1. And while this is my ground truth generated from PX. I'm sorry, so there is a mismatch with the notation there. What I call capital X here, I will correct this in the notes, is what I call X star here. So it's a random variable drawn from the prior, not the posterior. And here what I denote X1 is this X. So I have a sample from the posterior distribution, a function of the data. So the Nishimori tells me, so I'm there, that I can replace, sorry, I'm there, I'm losing myself. I can replace this posterior sample by the ground truth, which are instead drawn from the prior. So I replace this by this X star, and so I obtain the MMSE. So we have these two equivalent formulas for the MMSE, which are just a consequence of this simple identity. Okay? Perfect. So this really is the variance of the posterior distribution. Okay. So if I ever mention in the next Nishimura identity, this is where you should look at, and basically I'm doing simplifications by interchanging ground truth, like unknown ground truth parameters with a new sample from the posterior distribution. I can exchange them like this inside expectations without changing anything. This is an important thing. All right, so I just told you that now I want to introduce this high-dimensional inference problem that I call the Spike-Wigner model that I mentioned quickly at the beginning, but I haven't defined formally. But before doing so, I want to study a much simpler problem, a much simpler inference problem, which is called scalar denoising. And we will see that actually there is a deep connection between the two, despite that what I'm going to present to you here is extremely simple. The scalar denoising problem is an inference problem over a scalar signal. So you have this unknown. So from now on, I will use a star like this to emphasize ground truth unknown parameters to recover, to distinguish this from, let's say, an X that would be a sample from the posterior distribution. Okay? So I'm measuring, my data is this single scalar, which is just my unknown X star times a signal to noise ratio, which is this square root lambda, plus Gaussian noise. This is just a standard Gaussian random variable. Okay? So this problem is very simple. There is a single variable to recover. We have a single data point. Yet it's important to understand, and we will see why. So let me just give you an example. So if the X star you want to recover is a Gaussian variable itself, so you have a Gaussian variable you want to infer, which is corrupted by another Gaussian variable, which is noise, you can compute explicitly the mutual information, and it's a very simple formula. It's 1/2 of log of 1 plus signal to noise ratio times the variance of this signal, okay? I claim that the MMSC is the following, and how do I obtain this? I use the IMMSC formula. So I take twice the derivative of the mutual information, and this is very simple. You derive this with respect to lambda, and you get this, which by the IMMSC formula gives us the minimum mean square error. Okay? So very simple. Okay. So here there is a section where I prove this relation. This is also a denoising problem. You see, we have signal plus Gaussian noise. It's a bit more general because this is not necessarily a scalar variable in this case. When I put capital letters like this, which are not in bold, I mean generic variables, not scalar, not matrices, it can be anything. But it looks very much like the denoising problem. We have signal plus Gaussian noise. And so I used this formula to obtain the minimum mean square error from the mutual information. Okay. So this IMMSC formula that I just recalled you can be proven. I will skip the proof, but I recommend that you take a look. It's very simple. It's really about directly deriving, so writing down the definition of the mutual information, taking explicitly a derivative, and then doing some integration by part with respect to the noise variable. It's very simple, but the mechanisms that appear here are recurrent in this course. So I recommend that you try by yourself, okay? Or at least you understand what is written there. So this, I will skip the proof.
Sir, may I take a moment to request everyone to please switch on their camera? I will take 1-2 screenshots if possible. May I request everyone to switch on their cameras also? Okay, sir, you continue, huh?
Okay. So let me mention that another example. So before I considered the signal, which is Gaussian distributed, corrupted by Gaussian noise. Let's consider now that the signal is not Gaussian. It has another distribution. It is binary, okay? So this is telling us that with probability 1/2, the parameter we want to recover is equal to +1. And with probability 1/2, it is equal to -1. Of course, I don't know whether it was a +1 or -1. This is what I want to find back. So I'm trying to recover a random sign measured under Gaussian noise. Okay. You can, using the explicit definition of the mutual information that I write here, starting from the difference of entropy of the data minus the entropy of the noise. Remember the previous lecture. Here you can do a bunch of simplifications, and you will arrive at a generic formula, which you can derive. You get the MMSC. And in the case of denoising a binary variable, you obtain a slightly more complicated formula than before, which is now still with an integral there. You cannot fully simplify it. It remains an integral with respect to a Gaussian variable z. And it is the following. It's 1 minus expectation of the hyperbolic tangent of the SNR plus square root of the SNR times this noise to the square. And here you see it looks like I've done a typo. I'm writing an equality, and I have the very same formula, but there is no square here. This is not a typo. This is actually a consequence of the Nishimori identity. So if you do things correctly, you would realize that these two things are equal, and this is a basic simplification implied by this Nishimura identity I discussed before. Okay, so we have two formulas for the MMSE of scalar denoising problem. One when my signal is binary, and one much simpler when my signal is Gaussian distributed. So I can just plot these two functions. I will take sigma squared equal to 1 here. We'll take a standard Gaussian variable for my signal. I can plot these two formulas as a function of the SNR lambda and see how they look like. Let's do this. They look like this, okay? So this is this function for the denoising problem as a function of lambda, the SNR, okay? So there are different observations we can make here, okay? The first one is that these two quantities, they start from 1 when the SNR is 0, okay? And this is simply telling us that when the SNR is 0, so basically the data we have access to is pure noise, the only thing we can do is trust our prior, because we have no data, essentially. This is pure noise, okay? And we know it, because we are a Bayesian optimal statistician, so we know the value of this SNR. Forgot to mention, but in this Bayesian optimal setting, knowing the likelihood means knowing also the SNR, of course. So because you know that your data is just noise, you're not exploiting it, the best you can do is essentially exploit the prior. And the mean with respect to the prior in both cases is 0, because the Gaussian variable has 0 mean and our Rademacher variable here has also 0 mean. So the Bayesian optimal estimator when you have 0 SNR is just to output 0. And the error of such an estimator in average is 1. Okay? And then when the SNR increases, the error decreases as it should. Okay? So the other thing we can notice is that the Gaussian curve is above the Rademacher curve. And this is natural, right? Because the Rademacher prior is a much more informative prior than the Gaussian. A Gaussian variable can take any value between 0 and plus infinity. It has very small probability to be too large, but still it is a like a continuous random variable with an infinite support. Instead, the Rademacher variable is telling you that it's or a +1 or a -1. So somehow you have much more information, right? So it is natural to see that the Rademacher minimum mean square error, I mean, in the case of Rademacher prior, is below the one of the Gaussian case, okay? And the third thing we can notice is that these curves are very boring. They're not interesting at all, in the sense that there are nothing special we can notice apart from the fact that they are smoothly decreasing functions, but we don't see any interesting behavior. And by interesting, I mean, for example, a discontinuity or at least a cusp. You see a point where it would be non-analytic. We don't see any such behavior. It's just a boring, smooth curve in both cases. Okay. The reason that these curves are boring is that, of course, the problem we studied is way too simple. This is a very simple inference problem. There is no complexity, okay? So by complexity, I mean two things. And this is also what physicists mean when they, in statistical physics. Complexity means that we should consider inference of many variables. So we should go towards high dimension. And these variables should interact somehow. They should not be independent, because of course, if you are trying to infer unknowns which are completely independent and your data does not mix them, does not couple them in any way, you are simply trying to solve independent scalar problems. So we need many variables that are somehow coupled, that are dependent on each other through our observations of the data. Okay? And so this is where the Spike-Wigner model enters into play. Okay, so this is where interesting things will now happen. Okay, we hope that some more interesting behavior than this smooth MMSE curve will emerge, and this will be the case. Is there a question before I go towards the high dimensional problem?
Do we have any questions from the audience?
Okay, there's not. I will continue. All right. So here is the Spike-Wigner model. So memorize it, put it in your hand, because for the next 4 days, you're going to study it in very much details. Okay? So this is an inference problem where now the data, Y, is a matrix of size n by n. It's a symmetric matrix. The signal, the unknown parameters to recover is this x star. It's a vector of dimension n. The noise is a symmetric Gaussian matrix. Okay. And the way the data depends on the signal and noise is this model there. So basically what you do is that you take what you observe are noisy versions of the pairwise products of the entries of the unknown vector. Okay? You take a product xi star, xj star, you multiply it by a signal to noise ratio. You also scale down its amplitude with this 1 over square root n. I will explain where it comes from, where n is the dimension of this vector, x star. You corrupt this by noise, and this is your observation. And you do that for all the possible pairwise products between the components of the vector. Okay? So why is this called the spiked Wigner model? It is called so because a matrix like this, a matrix which is symmetric, whose entries are independent Gaussian, is called a Wigner matrix in random matrix theory, and we're going to study it in detail tomorrow. Okay? And this part, the signal part of interest, which we try to recover, is called a spike. It's called a spike because it's a rank 1 matrix. Okay, so matrix wise, you can write it like this: x star transpose. A rank 1 matrix like this is called a spike. So this is a spike model because you have a full rank noise matrix which is perturbed by a rank 1 spike, and you're trying to recover the rank 1 spike from the sum of the two. Is the model clear? Please stop me if it's not, otherwise you will suffer for the next 4 days, or it will make no sense to continue. So if the model is not clear, just ask. Okay.
Excuse me, sir. Am I audible?
Yes.
Sir, I have a question.
Go ahead, yeah.
Hello. Yeah. So xi star and xj star, you were telling that this is the unknown for the these symbols are for the unknown parameters, right?
Yes.
Okay. So if we are adding the x summation like xi and xj for the unknown parameters and adding with the zij, so like what is the its real like meaning and the significance? How like can we interpret from this? What is this exactly saying? Like I'm not getting it.
So sorry, I don't think I get your question. What your question is what's the meaning of this, or?
Yeah, like what is the role of this zij with this unknown parameter of xi and xj?
So okay, the zij here represents noise. It represents the component in the data. So this is the data that you observe. This is the only thing you know as a statistician. This is the unknown component, and this is the noise. Okay? You don't know X star, you don't know Z. The only thing that is given to you is this matrix Y. And your task, the inference task, is given this Y only, and the knowledge of how the Y was generated conditional on X star. So you know this model basically, but you don't know X star and you don't know Z, and you want to recover X star from the Y. Is it clear?
Okay, but sir, like one more thing in this same question, like how we are taking only xi star and xj star as a unknown parameter only for
No.
like.
No, it's not just xi star and xj star. You measure these yij's for every I and j running from 1 to n. You have many observations for
Yeah, okay, 1 to n. So for that, my main question is like, why only the product of x with I and x with j? Why not with another variable, like same variable? Why we are taking? Just because we are having the same matrix, that's why.
because we are having the same what?
Yeah, like I'm assuming like that we are having this operation inside a one matrix like Yij. That's why we are taking like the Xi star or Xj star, or is it having some different analogy?
So I mean, your question is why is the model like this, right?
Yeah. That's what I was.
Yeah, I mean, simply it's my choice. It's a model that I find interesting to study. Now I will give you applications of this model. But what I claim is that studying this precise inference problem allows you to understand very many practical settings that I will show you, okay? So assume that this is an interesting model. You could study infinitely many other models, of course. But I claim that this is one which is very rich, that at the same time you can fully understand, and that has many applications. Is that a valid answer?
Yeah. Okay.
Okay,
Thank you.
perfect.
I had one more question.
Yes, please.
What is lambda?
Yeah, lambda is like before. It's my signal to noise ratio. It controls the strength of the signal part, which is this rank 1 matrix, with respect to z. You see that if I take lambda going to infinity, basically my data becomes only signal. This becomes irrelevant, right?
Mm-hmm.
If instead lambda is 0, this is the opposite. Lambda equal to 0, there is no signal part anymore, and the data is pure noise. So the signal to noise ratio controls the signal part in the data. Okay.
So I imagine, as lambda goes arbitrarily small, does this algorithm work that you can recover x?
So we are going to study algorithms.
This is sneak peek, yeah.
Yeah, exactly. So the whole point of the course is to understand how well can I infer this part here as a function of lambda. This is the whole question.
Mm-hmm.
Okay?
Perfect.
So we will see that the answer depends on which algorithm you're considering and the cost you're ready to pay in terms of computation. Okay?
Okay.
So we are trying to first fitting up these equations as their model, and then we are going to test it in under various situations, like how it is suitable for different situations and circumstances in this segment.
Yeah. So it's a kind of abstract general model, and I will claim very soon that it is important for many applications which are relevant in signal processing, in machine learning, in many contexts. Yeah. Okay. Okay. So here is the model we want to study. Okay, that I wrote here in matrix form. So do you all hear me, or is it frozen? Hello?
Yes, sir.
We can hear you.
Hello, yes, sir, you are audible.
Okay, I'm back. Perfect, perfect. Thank you. All right, so this is our model. Perfect. So assume for the moment that it's an interesting model. I will show to you that it's the case. Let's assume that's the case. Let's write down, let's exploit what we've done in the previous lecture. Let's write down the posterior distribution. Okay? So the posterior distribution is written there. This is very simple. It's the prior. So I will assume that in this model, I will even simplify further this model. I will assume that the entries xi star were generated IID independently and identically distributed from my prior px. Okay, so this is a modeling assumption that I assume is correct. This is the setting we're studying. So my prior distribution is there. It's a product measure over all the components weighted by the correct prior times a Gaussian likelihood. Okay, so you see that for every observation Yij, I have a Gaussian weight, and this Gaussian comes from the fact that the noise Zij was Gaussian. Okay, so this is saying that the noise is Gaussian is the same as saying that my observations Yij were generated as Yij conditional on x star was generated as a Gaussian with mean square root lambda over n xi star xj star and variance 1. This is another way to rewrite the Spike-Digner model. It's exactly the same thing, right? Because this formulation is equivalent to say this. You see, adding a Gaussian noise of variance 1 to this shift, which is like a mean, is the same as saying that Yij, conditional on this, has this mean and variance equal to 1, right? Okay, so this is my likelihood. This is my likelihood distribution. And so, it's what's written there. I have a product of exponential, one for each observation, which I can put as a sum inside the exponent from the property of the exponential. I have an exponential of sum over ij of Yij minus square root lambda over n xi minus xj. Okay, this is this distribution there. Yij is a Gaussian with this mean and variance equal 1. So here is the mean and variance equal to 1. Okay, is it clear? And this is just the normalization of the Gaussians. Okay, and this proportionality symbol means that this is an equality up to a missing normalization constant that I should write down correctly. But is it okay for you? Do you understand the form of this posterior distribution? Prior times the likelihood of each observations. Okay? Perfect. Let me give you a few motivations. So there's been many questions on why is this model useful. That's a very valid question. So let me motivate it in different applications. So this model was originally introduced by statisticians around 2010, but it was studied earlier by people in random matrices as a simple probabilistic model for what we call sparse principal component analysis. So I think you all know what principal component analysis is. It's about taking an array of data, a matrix of data, and trying to find some principal components, meaning some relevant linear combinations of the columns of this data that you can think of as features, where the rows are samples. You are sampling points which have different features, and you are looking for linear combinations of these features that can explain most of the variability of the data, but using just one direction, just one vector instead of a whole basis of features. You want to find a special feature, which and this is PCA. And this is a model for PCA because you see, this is like we have noisy data. This is the noise component. And this is the hidden special direction. It's a rank 1 matrix. So we're looking for X star, which is a single vector, which will capture the information part. It's a special direction we're trying to recover. So it's like PCA. And if you assume that the entries of this X star are sparse, so it has many zero components, so this hidden direction that you're trying to find lives on a subset of the ambient space on a lower dimensional manifold. Only few components are non-zero. This is sparse PCA. Okay, so it's a very important problem in signal processing. Okay. Another problem I want to mention there is community detection in the stochastic block model. So I won't explain how the connection is made, but I will explain you what it says. The stochastic block model, so community detection, what it is, it's a problem, it's an inference problem, where what you observe is a graph of interaction between nodes. Okay, so you have a graph. And what you assume is that somehow in this graph, there are communities that are hidden. It means that some nodes can be kind of clustered together. They share some property, while some other nodes, they belong to another group. They share another property. So think about observing, for example, the graph of connections among people on Facebook. Okay. What you know is that on the Facebook network, there are people that vote on the left, and there are people, the voters for the right wing, left wing. Okay, and your hypothesis is that people with the same feature, so let's say that vote for the left, tend to be more connected to each others. And this is natural indeed, right? You tend to be friends and therefore to be connected on Facebook with people, more likely with people that have the same opinion as you, so that will vote the same party, right? So these are the two communities that you're trying to recover. And the inference problem is given this observation of the graph, which you can think as a kind of noisy data, because of course you will also be connected to people that vote differently than you, which you can think as a source of noise. It disturbs inference. Given this noisy graph, can you recover the communities? Okay, to which node, to which party a given node will vote for? This is a very generic problem. Or for example, in ecology, you can measure, you can observe that some species, which are the nodes on the graph, interact with each other. Some are predators, some are preys. Preys and predators tend to interact because one is hunting for the other. There are species that do not interact at all, etc. And given this graph of interactions between different species, you are trying to cluster the species into groups which have various meanings. Okay. Surprisingly, the theoretical study of this community detection problem is fundamentally linked to the study of the Spike-Wigner model. Okay? Somehow you can, I mean, at a naive, at a simple level, the connection, let's say, it doesn't look crazy that there is a connection with this problem, because you see, you can think of this as a kind of variable that tells you whether two nodes, if you now think of these components of these vectors as representing nodes on a graph, you are observing kind of interactions between nodes on a graph, which have been corrupted by noise, and you are trying to recover the state of the nodes. Okay, so if you now you say that every X star component can be plus or minus 1 to represent group 1 and group minus 1, or blue and red, or prey and predators, you are measuring graphs of interactions between these groups, and you're trying to recover which node belong to which group. So it's naturally connected to community detection. Okay. So, and which is a whole field in itself, by the way. Community detection, people do their entire career on studying this problem. And the way we understand the fundamental limits of inference in this community detection problem is through the analysis of the Spike-Wigner model. Okay. Another important model is high dimension. Maybe I will explain this one. This is a classical example. It's called the spike covariance model. So if you slightly generalize the Spike-Wigner model, where you say that now the rank 1 matrix is not anymore symmetric, so you have two vectors, u and v, and what you are measuring are noisy versions of the pairwise product between component I of vector u and component j of vector v. Then this model is equivalent to say that what you observe are Gaussian vectors, which are the columns of this matrix of observations, which have zero mean and whose covariance is basically the identity plus a rank 1 matrix. So you are trying, basically it's like if you have a noisy covariance matrix, and there is a hidden spatial direction in this covariance, which you're looking for. And the strength of this hidden direction is controlled by this lambda there. And this hidden direction is this vector u. Okay, so this is really a model for finding hidden direction when doing principal component analysis. Okay, it is also related to clustering, high dimensional clustering. You can read a bit, but I need to move on. So I hope what I convinced to you is that somehow the Spike-Wigner model is interesting. It's a very general model, and depending on the choice of the prior distribution for the signal, you will model this or that specific problem. Okay. There are many other applications. So I think that time-wise, it's been an hour. Should I continue a bit, Jaspal? I'm not done with everything I wanted to say, but I can also stop there and say a bit less. I mean, I don't have to finish everything every time. So.
Actually, sir, the team who is doing recording has to leave in 5-10 minutes. So you can take 5 minutes to wind up, and we can start tomorrow. If you want, we can start tomorrow, resume from here.
Okay. So if I have 5 minutes, maybe I can state the main results, one of the main results we're going to derive. So first, is there any question from anyone on this Spike-Wigner model? Okay. So the Spike-Wigner model, think of it as the most paradigmatic model for extracting hidden low-rank structures in high-dimensional, in large noisy matrices. And of course, given that data in modern applications always come in the form of large matrices, where there is some hidden structure there, it is very general. Okay, so that's the motivation for it. Okay, so what is the main result we want to get? This result is called the replica symmetric formula. So forget what the name means. This is not so important. This is just a terminology that comes from statistical physics. Historically, we call this kind of formulas in this way, but think of it just as a formula for the mutual information of the Spike-Wigner model. This is what it means, okay? So this theorem, which I have proven with colleagues during my postdoc, based on mathematically rigorous techniques we developed, which I will not explain during this course. Instead, I will show you a heuristic derivation based instead on physics tools, which you can then prove using other techniques. But I will focus on the physics tools. It would take a whole course to prove these kind of things, but trust me, this is a theorem. This theorem is telling you the following. The mutual information between this rank 1 matrix, the spike, the information, and the data, divided by n, okay, which is the same as the mutual information between the data and x star itself. So why is this equality true? Simply because the data depend on x star only through x star transpose, only through this rank 1 matrix. In case this is not clear, this notation simply means x star transpose, which is an n by n matrix. It's a row times a column. Sorry, it's a column times a row, so it's a matrix whose elements are xi star, xj star. Okay, so the mutual information between signal and data is given by a pretty simple formula, which is an infimum with respect to some parameter that we call q, that belongs to 0 and rho, where rho by definition is the second moment of the prior. Yes. Okay. The infimum of a certain function that depends on this parameter to optimize over and on the signal-to-noise ratio in the problem. Okay. And this function is called the replica symmetric potential. Again, this is just a name. It's a certain function which has the following nice form. So let's focus on this part here. So there is a very simple term there, which is just quadratic in Q times the SNR. And what appears here, now you should recognize, this is the mutual information of the scalar denoising problem under Gaussian noise. You see this x star here, you should not think anymore as the vector. For the vector, I use a bold variable. It's just a single scalar random variable drawn from the prior. It's written there. And this z is just a single scalar Gaussian noise. So this formula is telling you that somehow there is hidden in the high dimensional problem of interest, the Spike-Wigner model, a kind of reduction in complexity when in the so-called large system limit, when n goes to infinity, where n is parameterizing the size of the signal to infer, and therefore the size of the data matrix. This is an n by n matrix. So when the problem size goes to infinity, the very high dimensional object corresponding to this mutual information, this is a very complicated object, somehow reduces onto this simple formula. And in this simple formula, there is in particular something we recognize, which is the mutual information of a single scalar denoising problem. Okay? So this looks very weird. How the hell could it be that this high dimensional complicated problem where all variables interact with each other through the data could collapse on such a simple problem? So we will see first that even if this simple problem appears, the problem does not trivialize, okay, through this infimum operation here, which hides complexity. and interesting things can happen. So I will try to show you, to give you some, let's say, to try to convince you how does this happen, and we will see towards the last lecture. We will show this result and we will understand the mechanisms behind this reduction. What I want to say that I forgot. No, I forgot nothing, I think. So yes, so that's the main goal. One of the main goals of this course is to understand why is the computation of this mutual information reduces to such a simple problem there, okay? And this is really at the core of what we call the mean field analysis in physics. This kind of dimensionality reduction from very high dimensional problems to kind of effective low dimensional problems is typical from mean field analysis in physics and generally in what we call high dimensional statistics, in modern statistics. Okay, so we're going to understand that in the next lectures. Okay, I think that's enough for today. We will resume. Okay, I'm already late, so I will have to cut a few things, but tomorrow we'll spend at least 2 lectures on this chapter on random matrix theory. We're going to study the performance on this problem of a very simple algorithm, which is spectral PCA. So you can already take a look if you want. Okay, so then see you tomorrow, except if there are questions.
Is there any questions? So tomorrow we are starting at 11:40 IST.
Yeah. Perfect.
As in the schedule. I may also request everyone to kindly switch on their camera so that let us take one last screenshot for the day. If you all, sir, you may please stop sharing your screen so that we can take one screenshot.
Okay, you want me to stop sharing?
Do we have questions? I request everyone to please switch on your camera so that I can take everyone in one screenshot. Huh? Thank you.
It's nice to see real faces.
Yes.
Hello, everyone.
And I request that you may switch on your camera. It gives the lecturer more interest that if we are able to see, I think it creates more interest. So you may switch on your camera even throughout so that we can see each other and learn. So with these words, I would like to express my sincere gratitude to Professor GIAN Barbier to spend one full day with us. Thank you, sir. Thank you for your kind insights. And I would like to thank all the participants for patient hearing. And we will see you tomorrow at 11:40 a.m. as per schedule.
Have a good rest. It will be an intense.
Thank you, sir. Thank you, everyone. Okay, bye-bye.
Thank you, sir.